Okay, so good afternoon to you all, and welcome to the 2021 edition of the Open Day of the Center of Telecommunications and Multimedia of INESC Tech. Under the topic, so good afternoon to you all. I'm sorry, and welcome to the under the topic towards 6G enabled by edge intelligence. So my name is Luís Pessoa. I'm manager of the Optical and Electronics Technologies area of the Center of Telecommunications and Multimedia, and I will be sharing this event. So let me start by giving you some general information. So all participants will be muted by default. So if you want to ask a question, use the Zoom's chat or the raise hand reaction during the discussion periods. We invite you to keep your video cameras on throughout the event to make speakers and participants feel as more comfortable as if in a single room. So we are recording the meeting and streaming it in real time to the INESC Tech YouTube channel. So we will try to make presentations available in the website of the event after this meeting. So the meeting, as you can see, you have here the schedule, and there will be a first part dedicated to the CTM vision. Then there will be a 15 minutes break and a second part where there will be presentations from invited speakers and followed by a panel discussion. Let me once again thank you all for your participation, and we will now have the opening session, and Professor Jaime Cardoso, coordinator of the CTM, will be presenting now.
Okay, thank you, Luis. Let me see if I can share the screen.
CTM will be...
Luis, is the screen okay?
Yeah.
Yeah. So let me start by thanking you all for your presence here today in our Open Day. It's really a pleasure to organize this event, and I really hope that you can benefit from it. And I think the topic is really timely. So, and it has several highlights, several perspectives. And maybe the first one is on edge intelligence, why edge intelligence, and it can be discussed in, let's say, different perspectives. In a, let's say, maybe in a more profound way, in the AI perspective, it really makes sense to question the centralized model of AI. The all-in-brain information processing, it's really, for AI, it's probably not the best option. The research in neuroscience suggests that the neural networks controlling cognition are intrinsically connected, related with the parts that control the sensing and the motor skills. And it's this body map neural connections that make things happen. And therefore, it really makes sense to question the centralized model. I know that the mainstream in AI is probably for this simplified approach, centralized, but this, what is called embodied cognition, is gaining traction, and it's probably something to really pay attention in the future. Nevertheless, even not going on this direction and going for more pragmatic views and perspectives, it also makes sense to question the centralized version. In these times of data science and data-driven models, we could try to tackle the problems with decentralized high-performance computation with a lot of memory and everything centralized in cloud in these high-end servers. But and this provides, well, good solutions for many problems, but there are issues related with the security, for instance, or with the latency that are not well addressed with decentralized model. So in applications like autonomous driving, for instance, or the Internet of Drones, or any application where we have machines and human interacting, like for instance, I don't know, telesurgery, or in these working environments in general, where humans and machines interact, and for safety reasons, the latency is critical, the centralized model is probably not the best option. And it makes sense to consider this edge AI, edge platform, because it provides, I would say, a viable solution to this problem, offering this low latency computation close to the device, close to the data source, without relying on the central server to do the computation and to make the decisions. So I say that edge intelligence makes sense, makes decisions more locally, collect data locally, and offer these quick interactions between the devices in an efficient way, in a reliable way. So, and we can talk, I would say, into perspectives. AI for the edge, AI as an improver of the edge platform, AI helping on the organization, orchestration of the edge platform, providing better solutions, helping on solving, on optimizing the problems to have effective technologies there. And we have the opposite. We have AI on the edge, where we need also to adapt AI, the methods, the learning methods, the way that we use the data, the way that we train, and then the way that we do the inference. We need to adapt this to this new platform, device, edge, cloud, making the best of everything, and probably using new loss functions, let's say, new balances between this cost, reliability, efficiency, and performance for sure. So, and therefore, there is also a lot of work to be done in adapting AI for the edge. And then the question is also why bringing 6G to this discussion. I think it's clear by now, and it's accepted by many, that 5G, one of the key aspects that is missing in 5G is really this edge intelligence, powered by deep learning and machine learning. But this is, let's say, missing. 5G was a step in the right direction, but it really is not answering these critical applications that I enumerated before. And I think that edge intelligence is expected to enable and to be enabled by 6G and the future networks. So I think edge intelligence and 6G will together provide or help us to achieve this vision of ubiquitous intelligence. So this is why it makes sense to have this discussion, this open day about these topics. And I think it also makes sense to have CTM, the Center of Telecommunications and Multimedia, promoting this discussion. First of all, because we share the INESC Tech vision of bringing academia, making this bridge between academia and industry and society, and have this use-inspired research, both on fundamental aspects, on basic research and on the applied research. So solving real problems with cutting-edge research is basically what we do, and that's all about this topic, edge intelligence and 6G. So it really is a key problem for us in terms of this vision and mission. And more than that, our vision and mission, it really already captures a lot of the key aspects that are fundamental for this edge intelligence and this 6G communication problem. We already highlight our scientific driving forces are totally aligned with these key aspects of ubiquitous sensing, vision, precise positioning, low latency communications for sure, hardware, dynamic hardware, configurable hardware, and machine learning and the intelligence there. So we are all about this, For sure, we don't do everything that is needed for edge intelligence, and we should not aim for it, because then we will not do it properly. But we really address many topics that are fundamental, that are central in this problematic. And I think that we have the know-how and tools to have an important position in this field. And we also have the dimension. We are more than 100 collaborators, and then we are organized. We are organized in 5 different research lines that tackle then specific aspects of this vision and mission that we have. And I will just highlight 4 of these 5 because they are more strongly aligned with this edge intelligence and 6G. On the hardware aspects, I'm now trying to speed up a bit. On hardware aspects, we have the area of optical and electronic technologies that addresses the communications from this hardware perspective. So we bring together know-how, skills on electromagnetics, on optics, on electronics, on dynamic hardware, and they are put to the service of the communications, both optical and wireless, I would say. And more specifically, for instance, in terms of antennas, we do research on small antennas, on miniaturizing antennas, and then also on arrays of antennas, and these optical and wireless interfaces. And we also do signal processing for these. For instance, helping on beamforming of the antennas, and with also a focus on localization. On the hardware, on the platform, let's say, we do research on the analog domain, but also on this hybrid and mixed signal processing, mixing analog and digital solutions. And we have a special focus there also on the low power sensors and neuromorphic solutions for edge computing, as we will see today in a talk. And then we have also the FPGA and dynamic hardware providing solutions for acceleration, for instance. And then we have the laboratory supporting all these with the right equipment, with the right solutions to support all this research. On the wireless wireless network area, we tackle challenges related with, let's say, extreme environments, like the sea, like maritime environments, focusing on extending the infrastructure to the sea, for instance, but not only to the sea, also to other challenging scenarios like sport events where we have a strong concentration of a strong demand, a dense demand of networking, or catastrophic scenarios, for instance. So the main research here includes the topology control, the routing, the optimization of these, the resource management, radio resource management, the cross-layer optimization, and machine learning to the service of this, helping on this optimization. And you'll see also a bit about this today. Another topic that we could also highlight is related with the energy saving, energy efficiency, where since we have strong usage of networks, more and more traffic, the sustainability and the energy efficiency is getting central also there, and having low-cost solutions, eco-friendly solution is also part of our research. And then in 2 other research lines, and I'm more or less going to discuss them together, on multimedia management, audio visual content management, and computer vision. We address topics related with, for instance, this capturing, communication, consuming of multimedia content for different settings, for the creative industries, for sports, for robotics, for health, and so on. The adaptation, the description of content there is fundamental, and providing this really immersive consumption of the content. On computer vision, we perform research on fundamental aspects and also on applied problems. Computer vision has, let's say, achieved a strong impact and quality in narrow domains, in many applications, but is still facing fundamental problems, fundamental challenges there. Even the most advanced solution, they really fail yet in some basic, I would say, basic like this for us situations, and we are working on that. Especially, for instance, on what we call this open world settings, where the data that is seen when building the model is then different from the data that will be available when using the model. When we have this mismatch between the training, what we call the training data, and then the test data, that the model still face a lot of problems there. When we want models that are efficient, and efficiency again can be in different perspectives, memory, computation, energy, the performance still also suffers there a bit. So we also address those kind of challenges. And then we also address these challenges of this domain adaptation, where, for instance, we have a network of sensors, and that could be a network of cameras. And the cameras have different conditions, different settings, different properties, and therefore the statistics of the data is different between cameras. And we need to adapt also again the models for, maybe we need to personalize the model for each individual sensor. And we also work on this model adaptation, domain adaptation, data integration from these different sensors. And this is also central in CTM. And I would say that this brings us back again to the topic of our Open Day today. And I just want to finalize by acknowledging everyone. And I will start by the organization. Thank you all for making this possible, especially Luis, for being a true volunteer in organizing this event, and all the team behind Luis, for sure. Thank you also for the colleagues in center for sharing with us their part of their work. Teresa, Vitor, Felipe, Eduardo, thank you all. And for sure, a big thanks for our external invited speakers for sharing with us their view of the field and helping us to understand better and move forward. So a big thanks to António Hurtado, André Lourenço, Medi Beni, John Soldatos. And the final thanks go to Manuel Ricardo, representing the INESC Tech Administration, but Professor Manuel Ricardo is also a collaboration of the center and an expert in communications, and for sure the right person to moderate the debate and then to close the event. And I think a final word goes to everyone for being here and sharing with us this event and participating and making this better. With these different perspectives from the industry and academia, we have different backgrounds, and that helps us to have different views and to understand the problem in different ways, and with that to enrich the solutions. And yeah, I think that's all from my side. Thank you again, and Luis, the word is yours again.
Thank you, Jean. Okay, so we'll move forward. We'll start now this set of presentations from internal researchers, which brings our, let's call it, CTM vision on this 6G enabled by edge intelligence. So as a first speaker, we'll have Ana Sequeira, who is an assistant researcher at INESC, and where she is associated with the visual computing and machine intelligence research area of the center. And her main research interests include machine learning and computer vision for biometrics, presentation attack detection, mobile biometrics, border control, and explainable AI. Thank you, Anna. You are free to proceed with your presentation.
Thank you. So, good afternoon to you all. I believe it's everything okay with my screen.
That's right.
Okay, great. Like Luis said, I'm a researcher at the VCMI area at CTM, and I am here today to talk briefly about edge computing for identity and well-being. So firstly, identity recognition can be done in several ways. It can be done by using can be done using by what you have, what you know, or what you are. So the third one has a obvious advantage that something that is intrinsic of the person cannot be lost like a key, or be stolen or forgotten like a pin. So that is why we nowadays favor biometrics for identity recognition. In fact, we can use several biometric traits. We can have a set of anatomical traits, physiological traits, or behavioral traits. We only have here a few examples, but these traits, they need to take in account some basic requirements. They need to be universal, unique, permanent, at least to a certain degree. They need to be measurable. They need to achieve a certain performance. They need to be accepted by the user, and they need to be resistant to circumvention at a certain degree also. But the biometric traits, most of them, they go beyond the identity information. They provide us much more than that. They can provide us information about the gender, age, emotions, and even psychophysiological states of the individual, like fatigue, drowsiness, stress, and others. So biometrics nowadays is everywhere in our mobile devices, in so many wearable gadgets, even in our cars, and so forth. We have all those smart devices, and nowadays, thanks to edge computing, we can bring the computing next closer to the point of interest before it goes to a cloud or a server. So one great example of this kind of edge computing is the project vCard ID, which is a project in which INESC collaborated with ENCM, and some present and past elements of VCMI played a major role. So in this project, it was developed a fingerprint matching algorithm that was performed on the card. So this match on card technology was pioneered and put Portugal in the cutting edge technology in fingerprint recognition. We also have an example of the automotive project, which is an ongoing collaboration between us and Cardio ID, ISEL, and Lusófona. And this is another great example. You will hear some more details related to this later, but just in brief. So the driver simulator developed uses ECG and video information to monitor the driver state. You can see in this small example, so there is being done an estimation of the head position, also some features of the face, and all this is very relevant to the detection of drowsiness in a driver. So important. Another example we have is the Mikos project. So here we have a very delicate situation of very vulnerable patients, and this is an example of how to monitor not the identity but the well-being of an individual. And the main focus here was to simplify on the medical artifacts around these so vulnerable patients. So we can see here an example of less intrusive heart rate detection, or the monitoring of the pulse and the respiratory rate, for example. And these are very good examples. So in our area, we have developed other works that are not yet so close to the edge, but they are very close to it, and we hope they will be adaptable. One is the emotion recognition from face images, as you can see, and this is now a very hot topic and can be used in many areas. We also have another richer demonstration where we can determine gender or age and gender, and even do a scene analysis, and even detect some potted plant that is behind the user, and many other features that I don't have enough time to show here, but it is very interesting and it's available. Another very important aspect nowadays is the real-time analysis of face images for machine-readable travel documents. So here we have an example of what is acceptable and not acceptable for the specific problem of head pose. And we can see in this demo video that whenever our student moves, it gets information about the deviation of the head pose according to the 3 axes, and this is sensitive to deviations of greater than 8 degrees, which follows the guidelines of the ICAO. This can be applied in many applications. So other works that have been done in the group, they are related to anti-spoofing, and like already mentioned by Jaime, about how can models deal with unknown attacks in real-world deployment. Also, if we are able to explain the decisions to the user by explainability of AI for biometrics, we can also increase the trust in the systems and the acceptability from the user. So this can also be applied in mainstream applications nowadays, like border control, where it needs to be done the recognition, the anti-spoofing, and the explainability all at the same time, or in mobile biometrics. Thank you so much for your attention. You can reach out to us or gather more information about all these works and others of the area in our website. Thank you.
Thank you, Anna. Very interesting. So is there any question from the audience? I don't see any in the chat right now. If you want to ask a question verbally, just raise your hand. Well, I can ask you a question. So I see that you focus a lot your presentation on the edge intelligence, but what about its relation to 6G? What do you think could be potential benefits for biometrics in next generation networks?
Well, the potential is huge, as we already seen. So we are still in 5G, but for biometrics, this is huge because we deal with very large databases, and there are several applications that can be so useful in real time, like surveillance for suspect the recognition and identification in quicker time for border control, access to spaces like football stadiums or concerts or other places, and with a better communication that will be available and potentiated by the 6G, all this new world will be open to these applications that are uh, about to happen.
Okay, Anna, thank you very much. Very interesting. Okay,
Thank you.
so thank you. So we can move on now. Our next speaker is Teresa Andrade. So Teresa is an assistant professor at the Faculty of Engineering of University of Porto and a senior researcher at INESC at the Multimedia and Communication Technologies area of the CTM. So her main research interests include context awareness, mobile and adaptable multimedia applications in heterogeneous environments, 3D and multi-view video streaming, quality of service and of experience in multimedia services, and Internet of Multimedia Things. Okay, Teresa, please proceed with your presentation. Thank you.
Hi, thank you, Luis, for the introduction. So I'll start sharing my screen. Please let me know if you can see my presentation.
It's
okay. So hello, everyone, and welcome to this presentation. My name is Teresa Andrade, and I'd like to welcome you to the presentation concerning IoT in multimedia. So we'll start looking at the concept, what it is, then the requirements and fields of application, then a very brief look at what is going on in standardization and research that is relevant to IOMMT. Okay, so IOMMT basically is the set of connected digital equipment, services, interfaces, resources that deal specifically with multimedia content. One can say that it stands for media-centric services and devices in a connected world where data is confined to multimedia. So it is in fact an extension to IoT, as one would expect, and it is driven by the great popularity of multimedia-enabled connected devices and sensors. So if it's really related, why bothering to define it? Well, essentially because the multimedia things present quite different characteristics and demands. Because large amount of data are generated and usually heavy processing tasks are involved. We know that uncompressed video data, for example, can arrive very quickly to hundreds of megabits per second, and thus compression is paramount, as well as the processing power needed to achieve it. As well as we saw previously, the use of artificial intelligence tools to understand media data in an automatic way is growing faster and faster, and it also demands large processing capability. So the expectations are that such processing can occur locally so that decisions and reactions can be made fast, efficiently, and securely. And we can say that this is quite different from the situation in conventional IoT, where limited functionality is offered, such as linear data acquisition and on-off actuators. The media entities that we are that will have in IOMMT, besides the multimedia information, we will have sources of data and receivers of data, and the sources of data can be anything that generates multimedia information, such as a microphone, a camera, musical instruments, and so on, and receivers of data, anything that can process and show, present multimedia data. Some of them can be simultaneously both sources and receivers. Such entities pose a number of very stringent requirements on the available IoT infrastructure, especially due to the large bit rates that they generate, the real-time constraints, and also security aspects, which are very important when dealing with multimedia information. And when comparing IoT with IOMMT, well, we can see that it's clear the imbalance that exists at all levels, and basically due to the nonlinear, bulky, real-time, and delay-sensitive nature of multimedia data. Well, at this point, you could say, well, tell me something I don't know, as these kind of requirements are typical from traditional multimedia applications and services. Well, but there is a big difference, and the difference is on how information, essentially on how information will circulate in an IOMMT world. It is expected to have massive multi-point-to-point communication, instead of the traditional point-to-point as in streaming, or point-to-multipoint as in broadcast or multicast. As well, the way as the processing will happen, instead of being centralized, it will hopefully be distributed. And so it's expected that edge processing will have a very crucial role in this sense. So this is illustrated in this picture, the traditional one versus the expected IOMMT, where the processing capability will be distributed. Well, the fields of application expected, besides the traditional entertainment domain, all of the other fields that are being addressed by IoT, from health, smart cities, security, industrial environment, sports, agriculture, intelligent homes, and so on. In all of them, the addition or the use of multimedia information is expected to bring many benefits, because it really provides a larger source of knowledge, of information. Well, this, as we saw, the demanding requirements and the large area of application, they pose considerable burden on the existing IoT infrastructure, and it is thus imperative to try and alleviate such burden to guarantee coexistence between IoT and IOMMT. And in this sense, edge computing play a crucial role, providing the ability to decide and act on the spot. Media analytics is thus expected to depend heavily on edge computing. Well, nevertheless, there are different situations, and those situations may demand different solutions to decide what to process and where to process. And it is thus imperative to be able to communicate and interact efficiently with all the media, with all the multimedia things. And this is where standards can come in. Some work is ongoing, namely in IEC, with the Internet of Media Things set of specification that are defining interfaces, protocols, and formats to enable what I just said in the previous slide. So the recently released specification is divided in 4 parts: architecture, format, discovery and communication APIs, formats, and conformance and reference software. Nonetheless, this ISO specification is mostly concerned with the efficient processing and storage and manipulation of the bulk of the huge amount of multimedia data that is expected to be generated in IOMMT, and is not looking specifically at some requirements of a very big part of multimedia, which is the media production industry. This kind of requirements are being covered under the umbrella of the Advanced Media Workflow Association, with the development of the Network Media Open Specifications and MOSH, which are basically a set of APIs that enable finding, connecting, and configuring media equipment in a connected world. Let's just very briefly look at some examples of use cases where these two standards may find application. The first one, smart video surveillance, with on-site processing, decision, and actuating capability, so that comments can be sent to the camera to control settings, or to start analyzing the video to detect persons, or to detect anything else in another situation, or to analyze the important parts of the video and send only those important parts, or even to generate metadata and send those metadata. So it's necessary to maintain an interaction, to send controls, to send commands, and to instruct the devices on how to proceed. The other use case is media production, setting up remotely a media production workflow, where it's necessary to discover, configure, and triggering connected media equipment. This is illustrated in this slide. On the left, we see functional architecture of this kind of remote post-production. And this was developed in a research project in which CTM, INESC and CTM was a partner. So we can see the existence of the typical publish-subscribe paradigm that exists in IoT, where we have a broker that mediates and access all the different media resources. And on the top right, a very simple example of such remotely produced, remotely workflow for producing or for switching between live sources and archived material, and then producing at the output two formats for the program, one for live streaming and another one for storage. And this can be done totally remotely using the protocols, the APIs, and so on that are being developed in the referred standards. So there are still quite a lot of open challenges for a full implementation of IOMMT, not only at the media manipulating side, for example, with the need for more efficient codecs, but also at the network level side for the efficient access to wireless and cellular networks in order to try to achieve low latencies and real-time transmission, but also at the security level in order to be able to certify equipment and also to guarantee that for example, cameras in smart video surveillance scenarios are not hacked and content is not compromised. So the ongoing research efforts on many aspects, among which I have here selected some, are very relevant to IOMT, even though they are not specifically targeting IOMMT. So I leave you here with some references for the sources of information. And I have nothing else but thank you for your kind attention and make myself available to try and answer some questions that you may have. Thank you very much.
Thank you very much, Teresa. Is there any quick question from the audience? Okay, so if not, I can ask you, what do you think is the biggest challenge for the implementation of IOMMT? So you mentioned a few of the challenges. Which one is the greatest in your opinion?
Well, definitely the possibility to instruct media things in a very dynamic way is one great challenge. Due to the limited network resources and the delay sensitiveness that these kind of operations have. But I think that it will be much more difficult to implement this at the professional level in order to try to profit from the large amounts of user-generated content and use it in a very dynamic way to produce live content to be distributed on the spot in that same time. So I think it will be quite challenging to achieve that. And edge computing, but as well 6G will be fundamental to achieve that.
Okay, thank you. So I see some questions came just now, but we are behind schedule, so I hope you can discuss or email Teresa, please. Thank you once again, Teresa. So we will now move on to the next talk. So the next talk will be given by Eduardo Almeida. So Eduardo is an assistant researcher at INESC and a PhD candidate at the Faculty of Engineering of University of Porto. So he's currently pursuing his PhD on traffic-aware and manned aerial vehicle placement for aerial wireless networks. And his main research interests include aerial wireless networks, UAV placement, and reinforcement learning. So Eduardo, please feel free to proceed with the presentation.
All right. I hope you can see my presentation.
Perfect. Thank you.
So good afternoon, everyone. My name is Eduardo Almeida. I'm going to present the research work being developed at the Wireless Networks Research Group at CTM, entitled Traffic Aware UAV Placement Using Deep Reinforcement Learning. So in recent years, aerial wireless networks have emerged as a promising solution to provide on-demand wireless connectivity in a myriad of scenarios. For instance, in temporary credit events, which were a scenario that was addressed in the WISE-HD project, there are lots of users which are concentrated on a predefined area, and they have specific quality of service requirements, and they are generating a variable and dynamic traffic demand because they are moving around the venue and generating traffic which is variable over time and over space. And in these scenarios, we can greatly enhance the capacity of the existing network by deploying a set of UAVs, so drones that are carrying onboard Wi-Fi access points or cellular base stations, and they can physically move and position themselves in order to follow the crowds and provide more coverage and capacity to the users that require them the most. On the right-hand side, under the right figure, we can see some emergency scenarios that are being addressed, for instance, on the ongoing European project Respond Drone. And in this case, we have multiple teams of first responders that are handling the emergency, and they need to communicate among themselves and with a central commander. So we can deploy also a set of drones to provide an instant and on-demand connectivity to those users, and to replace the existing base stations which may be damaged or overloaded in that emergency scenario. So how is the deep reinforcement learning problem modeled? So we start with an agent, which is in this case, it's the UAV that we want to position. And we want this agent to train and to learn what actions to take on the environment for a specific state in order to maximize the cumulative reward over time. This reward is a measure that evaluates the quality of the action taken on that particular state, which is fed from the environment to the agent. And so the higher the reward, the better that action was. So the objective of the agent is to learn what actions to take in order to maximize this reward over time. When we combine the reinforcement learning with deep learning techniques, we have the deep reinforcement learning model. And in this case, we can use neural networks as function approximators for instance, the state, the action, or the value provided to the agent, instead of having to manually derive those same functions. So we can address more complex problems than we could if we just used reinforcement learning. Of course, there are some advantages and disadvantages when we use deep reinforcement learning to solve this problem. But the main advantage is that the UAV, that the agent, is able to autonomously learn and adapt. So instead of having to manually figure out what models are most suited to the characteristics of that scenario, we can just let the agent learn those same characteristics and adapt to them accordingly in order to achieve the objective that we want to solve. Also, the agent is able to learn from experience. So every time the agent makes a decision and receives the corresponding reward, it is able to provide more better actions in the future, because it can learn from the mistakes that it made in previous actions. Most importantly, we can also use real-time network performance metrics to drive the training process. And in this case, instead of relying on estimates or approximations of this performance, we can instead collect these performance metrics on real time and use them to model either the reward function or the observations that are driving the training process of the reinforcement learning. The disadvantages are pretty much the same as the deep learning disadvantages. So these require high computational resources, and we need to tune the hyperparameters of the neural networks. And in the case of reinforcement learning, we need to balance the trade-off between exploring new actions that may lead to better rewards and exploiting those same actions in order to achieve the objective that we want to solve. So in this slide, we can see the proposed algorithm that we are working on to position a UAV that is serving a set of users on the ground. So we are modeling this problem as a deep reinforcement learning problem. In this case, our agent is the UAV that wants to learn where to position itself in order to maximize the utility, the network utility of the users. And to that end, we also have to model the state as a function of the observations taken from the real-time performance metrics collected of the networks, such as the characteristics of the traffic demand, where the users are, and so on. And those are the observations that we use to that the agent wants to learn to make actions according to that state in order to maximize the network utility. In this slide, we can see some results of our algorithm. So we trained this model using the INESC simulator, and we tested this on 100 different scenarios, so different combinations of traffic and position of the users. And then we plotted the cumulative distribution function of the network utility on the left-hand side. So we can see that our solutions are the ones on the right. So they are much better than our baseline, which is the purple line, and corresponds to the baseline on which the UAV is positioned in order to minimize the average distance to the users, which is equivalent to say that it wants to maximize the average signal-to-noise ratio to all users. So we can see that our network utility increased up to 2 times in some scenarios. And on the right-hand side, we have another plot where we plot the network utility as a function of the diversity. So this diversity essentially tells us that if this diversity is closer to 1, it means that our scenario is more heterogeneous. So there is more differences in the traffic generated by one user to the remaining one. So there is more heterogeneity. and 0 is the opposite, so homogeneous scenarios. We can see that while on the homogeneous scenarios, all solutions are pretty much equivalent because there's not much you can do to improve the network performance. On the heterogeneous scenarios, our solution achieves much better results than the baseline, almost up to 1.6 times more network utility than the baseline. So as a conclusion, we are working on this novel UAV placement algorithm that improves the network utility on both temporary credit events or emergency scenarios or other scenarios that require aerial wireless networks. And the main benefit of this solution is that it is adaptive to the scenario dynamics. So the agent is able to autonomously learn and adapt to the characteristics of every specific scenario. We can also combine the offline training made in simulation, for instance, and then deploy this model online. But instead of having to train itself from scratch once again, we can use the pre-training that was made in simulator on the online deployment, while still making the model reactive to new changes that may arise during the deployment phase. And our next steps will be to evolve our work from one UAV to multiple UAVs that need to cooperate among themselves to achieve the same objective. So thank you for your attention.
Thank you, Eduardo. So I've opened now the talk for questions. Are there any questions from the audience? So in the chat from previous talk. So I can make a question to you. So which are the main challenges that you anticipate related to going from single agent to multi-agent architecture?
Yes, there are some challenges that we will have on the multi-agent problem that we didn't have on the single agent problem. But the most important challenge is that we need to verify how we want to model this problem. So the simple solution would be to model these multi-agent problems as n independent single agent problems. But the obvious problem is that the UAVs will not cooperate among themselves. So we will, instead of achieving a global optimal solution, we will achieve n local optimal solutions, which may not be what we want. So we need to figure out how to model these reinforcement learning problems for multiple agents, how to derive a reward function that affects all of them. And the same goes for the observations. So we need to think about how we can scale n single agent problems into one global optimal multi-agent problem.
Okay, thank you. So one more question that just came. Are you testing this solution already on the field or in virtual environments?
We are working on using INESC simulators, so in a virtual environment. But this model can be easily deployed online because the code is essentially the same. So instead of using the INESC simulator to model our environment, we can deploy this on the real world and make this process of collecting the observations and giving the reward. But in essence, the model is pretty much the same. So if it works on simulator, it will almost work on real time, on a real environment. But to answer the question, we are just working, as of now, we are just working on the simulator.
Okay, Eduardo. Thank you very much.
Thank you.
Okay, so we'll move on to the next presenter. Sorry. So our next presenter is Vítor Tavares. So Vítor Tavares is an assistant professor at the Faculty of Engineering of the University of Porto and a senior researcher at INESC, namely the Optical and Electronic Technologies area of the CTM. So his research interests include low power, mixed signal and neuromorphic integrated chip design and biomimetic computing, CMOS RF integrated circuit design for wireless sensor networks and large electronics. Victor, please move on with the presentation. Thank you. We cannot hear you yet. Can you unmute?
Now you can hear me. I'm sorry, I forgot to switch on the micro. Can you see the slides?
Yes, it's great. Thank you.
Great. Good afternoon, everyone. Thank you, Luis, for your introduction. My presentation will be more focused, a little bit focused on a project that we have been developing at INESC in collaboration with Sanimat at UNL in Lisbon. The name of the project is Neurooxide, and the person that we have been collaborating more closely is Azal Yazder. Her name is also on the presentation, and she's an expert on fabrication and characterization of memory cell devices. Okay, so this first slide, I don't need to talk much about it. My life is facilitated from the last presenters. We already know by now that we need to decentralize artificial intelligence and bring it close to the edge. If for nothing else, to avoid safety hazards. And if we take the self-car driving example, we cannot wait for higher distance computing platforms to decide where the car should go. And so all that intelligence that needs to come back to closer to the interface with the real world, if nothing else, due to safety, as I said before. Okay, so but we cannot. Modern age AI is fantastic. Is everywhere, as we know, much due to new AI algorithms such as deep learning and reinforcement learning. But these algorithms work well if you have big amounts of data and good communication networks to interchange and share data between different levels of the system. And this doesn't comply much with what is needed at the edge, because at the edge, as was mentioned before, we have limited resources. But I would like to emphasize also that modern age AI wouldn't be much if we wouldn't have powerful computing hardware available for that. And CMOS is on the front line on this respect. And I'm putting it in red because I will focus more on the hardware aspects of computation than anything else. Okay, if you take this image on the right as an example, so it's basically a control flow architecture, a standard what you have on your PCs typically. We have a memory bank separated from a central processing unit, and we have kind of an overhead of communication between memory and CPU because we share a common bus. And so this overhead creates latency in the system, and also put some tools on energy consumption. And all of these problems need to be addressed carefully at the edge, because again, on the edge, we have limited resources, and latency again could be a problem in terms of safety. Okay, so next generation AI, what many experts have been saying, is that we need to go to other algorithms that will be able to learn with less and less examples, so that the amount of data that we need to use is small. They should be able to learn with unsupervised, in an unsupervised fashion. Also, bring some cognition also to the systems, get them more smart even. But probably this will also demand new hardware paradigms, if not more, to avoid this problem of the control flow architecture that I just discussed. So one way to move forward in terms of hardware architectures for the future AI, there is a lot of research in a way to address the problem of memory bandwidth. So the time that it takes to address the memory, put data there and retrieve data from there. So the best way is to actually bring memory close to the processing side. And one of the things that has been proposed, and people are working on this also, is to actually stack layers of chips that will be dynamic RAMs. Okay, and then we use through silicon vias to interconnect these different layers, and we can put the logic at the bottom. So we have chunks or vaults, as they call them, memory banks associated with a logic circuit, and then we can build complex systems with many volts and many logic blocks. So in a sense, what we are doing again is bringing memory very close to the processing. We can also do kind of a distribution of processing in a given space. So we can have some processing together with some memory distributed in a space. And the space here you can think of as a chip, an IC. Okay, and that's what I have in mind when I'm discussing, when I'm presenting these slides. And then you can also build kind of a network on chip to communicate and distribute data among these different blocks and build your machine learning networks this way. Another alternative is actually think about a new device, which is not new anymore, but it's kind of a multifunctional device that can act as a processing element and the memory at the same time. And actually switching resistors were found to be able to perform more or less this that I have just mentioned in 2008. Okay, and they actually mentioned the results. It was at HP, by the way, and they referred at the fact that those switching resistors have kind of a behavior similar to memory resistors. I will call them memory resistors from now on, but I would like to raise the, the fact that actually the term memory resistor is kind of controversial, because there are many people that argue that memory resistors were not found, they don't exist yet, or maybe they will never exist. Anyway, what is very interesting about this is that you can think about, you can look at this device as a resistor, okay? A resistor that I can program its value with appropriate, electrical settings. Okay, and after I remove those excitations, the final resistor value, the state of the device, will be kept, and whenever I go and measure it, that value will stay there. So it's a memory. But you can also change it continuously. So it can have an analog memory with some processing capabilities. I have here an example of a crossbar memory using those devices, the memory resistors, and actually you can do dot products with this very easily. You can think of these devices as the weights of a matrix, and you can put a vector of voltage here, and you look into the currents at each column, and you'll have the results here at the columns will be the final dot product, and you have it on the fly. Okay, so it's very, very, very fast. And since these devices can be very, very small, you can have a high density of dot products there, and dot products is probably the operation that you do more on a multi-layer network, as I show here. Well, the dot products will happen here. This will be the matrix of weights, and you do the dot products on the outputs of the previous layer. So one way to see it. So in order to come and bring hardware more to the edge, maybe, and I'm not saying it should be, but neuromorphic computing could be one of the routes. Okay, it's more brain inspired. It's event-based processing in a sense. What I'm saying is that information is encoded in time. So we just use very short pulses to codify or to make a signal where something happened. So the information is in between the time spacing of the pulses. Since they can be very dispersed, and if the electronics only reacts to the pulses, so it can be very, very power efficient, okay? And a network like this that uses only pulses for computation, we simply call it spiking neural networks, okay? Actually, very interesting enough to know that memory systems can also, show some kind of similar synaptic learning as you see in the brain, typically like spike time-dependent plasticity, which apparently plays some role in learning in our brains. Okay, reaching to the NeuroOxide project, the main aim of this project is actually perform full integration of systems using memory resistors and supporting electronics with the same materials, so that we can use the same processing steps for the electronics and the memory resistors themselves. Actually, they will be fabricated at the very same time, layer by layer, okay, as we do similarly if we want to do the parallel with CMOS fabrication. Okay, and the materials we are focused on are amorphous oxide semiconductors, more precisely amorphous gallium indium zinc oxide, AGISO, AIGZO, and those kind of materials are the ones that are being used, for example, for the flat panel displays that you have now in front of you. Okay, so the basic idea is to minimize the interface problems that you have when you build memory systems with one technology and electronics with another technology. Also, this fabrication process is very low temperature and it's very low cost. It's much less complex than building with CMOS silicon systems. So the phases of the project means coming up with the memristors using the same material as the TFT. TFT means thin film transistors, or TFT can be thin film technology. That's what this technology is about. Okay, we have to come up with models for those devices in order to be able to design and build electronics with them. And we also built, and I would say it's one phase of the project, an infrastructure in professional CAD design tools for IC, in order for us to be able to do simulation and layout design that will define the masks for future fabrications. Just to give you an introduction here, you can see here a memristor, okay? Magnify there's a matrix of memristors here. And you can see that you can control the conductance of this device. This is current versus voltage by adequate electrical settings, okay? And so it's kind of an analog memory. And we have high resistor value, low resistor values also. Furthermore here, I'll show you something more close to what is expected on a spiking neural net. Okay, so we can use just pulses to program the memristor. So if you have a train of pulses that are positive valued, the conductance can be increased. And if you use negative pulses, I mean a train of negative voltage pulses, you can actually decrease the conductance. So this is kind of a learning procedure that will depend on the density of pulses that will be applied to the device, okay? And actually, I'm not going to much on detail here because we don't have much time, but it's kind of a short and long-term memory capabilities of these devices to make them very interesting for spiking neural nets. Okay, in terms of modeling, I'm not, well, I just want to show you here that actually the memory is a dynamic device, okay? We can, in a simplistic way, we can model it this way. So you can see that there is a current, a conductance multiplied by a V. It's almost Ohm's law if this was a constant. But actually there is a parameter here that we call a window that, you know, is dynamically adjusted according to the either voltage or current that we apply to the device. And we have been advocating for some time for research purposes only to use black box approaches for the modeling, typically data-driven systems, ANMs basically. And in this case, we have used the multi-step neural networks, you know, architecture, let us say it, or configuration, which is very recent, and it is allow us to capture the underlying ordinary differential equation that governs the response of the device. And here you can not see it very clearly, but this would be, you know, the dynamics from the device itself, and this is what is predicted by the network. It's still a little bit Mickey Mouse data, but already gives good hints that this could be an interesting direction. But I want to stop here just 1 second to say the reason why we move into black box approach is basically because, you know, this is still very immature kind of technology. Everything is changing very fast. And so this is a fast way to build a model. For industrial purposes, not that compact, but for free research is very good. Here, I also show you the transistor side, okay? You have here the structure. We again do modeling using neural nets, and you have here the results of different, you know, even the dynamics and the response of the device. And you have here a picture of the latest, you know, full integration of memristor and transistor on the same process. We are now characterizing it, and the final chip can look like this. This is not the same, but basically the substrates can be plastic, and you can see here an IC chip that we have made in the past with TFTs. Okay. Just to conclude, another concept level testing that we want to do in order to basically demonstrate the concept. We can actually use the memristors as a switching resistor in this case to produce different logics, okay? The imply or material implication is one procedure, it's not the only one, but that's the one we are trying. So we can use pairs of memories to build any logic that we want, and we can have a matrix to build a complex logic circuit, right? And this is really a good concept level demonstration of in-memory computation logic, in the sense that we can program the logic with using the individual memories, and the result of the logic is stored on the very same devices. So it's actually a good show on these abilities. Okay, and so this would work like an FPGA. But just to say that not only advantages on these things for sure, as you would expect or suspect, we can build, circuits, or we can only build circuits using a single type of transistor, which is an extra difficulty, but it can be done. Okay, so as a conclusion, for next generation AI, we need to do something on the network level and algorithms, probably not me, but on the hardware side, there are new paradigms that are coming up, like in-memory computation, event-based computation also, that probably will help to bring more close, computation to the edge. So I hope you have enjoyed the presentation.
Thank you, Vitor. Thank you. So is there any question from the audience? I can make a question. Oh no, just one came. So how much information can we store in these neuromorphic chips?
First of all, let's start in principle, since the memories that could be a continuous of memory. So it's an analog device. You have the first thing, you have no resolution problems, okay? But you can think of this matrix, for example, for dot products. Let me show, like this one. This device can be very, very small, so nanoscale. So you can put millions of them in a chip. But now the problem is that, and that's where the corner points come, is that building the devices, you can do it very small, but then the context to the device is a problem to make them uniform. I mean, from device to device, have good performance on the context, and eventually you will be, let us say, the limitation will come from the interconnect of the metals, because there will be limits on the spacing of metals and the width that we can build them, and that will be the limitation of the size of this device. So basically the same limitation, typically, if we can go as low as modern technology in CMOS, the limitation would be similar in respect to the interconnectivity, the one we have with DRAMs, okay? But this can be very, very dense.
Okay.
I don't know if I answered the question, but...
Thank you, Vitor. Thank you. I see a few more questions in the chat. So I can pick one. So what is environmental limitations, heat, vibration, etc.?
Environment, heat, vibration. Okay, as I said, I don't have those results yet, okay? Bending, if you use a flexible substrate, bending will pay some toll on the performance of the devices, but they are so small that, macro bending will be nothing, but bending on the device shouldn't be a big problem. Environmental, well, if these devices are exposed to the environment, of course, they will react with it. So, but we can use passivation on top of it. Okay, temperature is a trick problem, because temperature also plays some role on the memories of the device. So to put this in an industrial environment, we need to be careful with that. Okay, especially if it's in a car where temperatures can rise to very, very high values. This could be a problem. But in any event, we can also always put this inside of a case. If it is for a car, for example, inside of a case that you can climatize the case. And typically we do that with electronics inside the car. With FPGAs and everything, we can climatize the box. But that's a problem, yes.
Okay, Vitor, once again, thank you very much. So we need to move on with the event, otherwise
okay.
it will be very interesting to keep discussing. So we will have a break now. So we are a bit behind schedule. So let's resume at 15:35. So 12 minutes break. So we'll shorten it a bit. So we'll play a video during the break if you are interested. Thank you. So welcome back, everyone. So we'll resume the session now. So we will move on to this part of the event where invited speakers will bring their vision. So the first presenter will be Antonio Hurtado from the University of Strathclyde. Antonio Hurtado is a Turing AI Fellow and Senior Lecturer at the University of Strathclyde Institute of Photonics, where he is currently leading research programs on neuromorphic photonics. So Antonio will bring us a presentation entitled Neuromorphic Photonic Computing with Lasers. So Antonio, it is now your turn to move on with the presentation. Thank you very much.
Okay, thank you very much. Thank you very much, Luis, for the kind introduction. And thank you, Luis, and the rest of the organizing committee for inviting me here to introduce our research at Strathclyde on our work on neuromorphic photonics, or the use of photonic technologies for neuromorphic computing, for brain-inspired computing. So I'll just try to bring my pointer out. For some reason, it's not working. Okay, now it seems to be working. Can you see my slides all right on my screen? Okay.
Perfect. Thank you.
Okay, thank you very much. So as said, I'm from the University of Strathclyde. This is in Glasgow, in the United Kingdom, in Scotland. And this is a brief outline of my talk. So my talk is about neuromorphic photonics. So that was somehow a bit introduced in the last talk, in the previous section, neuromorphic computing. But I'll just dedicate a few moments on the motivation behind our work, what it is when we're talking about neuromorphic photonics, and what it can be used for, and why we are interested in using lasers for this particular technology, and specifically a type of lasers which is called VCSELs, vertical cavity surface emitting lasers, which perhaps you might know much about them, but they're ubiquitous in our society, as I will mention in a minute. After that, I will just talk a bit about the results of our research in recent times, and basically how we can model, how we can emulate our biological neurons with VCSELs and lasers at ultra-fast speeds to build ultra-fast photonic spiking neurons, and how we can use these spike processing elements for do computing, neuromorphic computing with photonics towards the spiking neural networks implemented with light enabling technologies, and also a few lines on our work on photonic recurrent neural networks with VCSELs, the development of reservoir computing systems for specific applications with these technologies, before I finish with a summary of my talk and an outlook. So the motivation for this work, so I guess we all know that the developments in computing technology have been amazing in the last 40 years. So now CPUs and computing systems operate at amazing speeds and can do all this incredible stuff that we are talking about, in the internet, processing, and have allowed the development of artificial intelligence technologies and the rest of it. However, although this has increased dramatically in the last 40, 50 years, it's starting to stall. And although we have reached very, very high speed processing limits, these do not come for free. So basically, these come at a very huge penalty cost. So we have the possibility to have computing systems that work really, really fast, that consume a lot of power. And that's also particularly a problem when we're talking about artificial intelligence, which requires a hell of a lot of energy for training algorithms and things like this. However, if you look at the other side of the scale, we have here the human brain, which, as we know, is the most powerful computing system there is. And counterintuitively, even if it's amazing to do, it's able to do all these amazing things, it operates at very, very low time scales. However, the good thing is that it consumes very little amount of power. And that's fantastic, because if you think all about it, this mass that we have between our ears is able to do fantastic things with very low power. If it requires more power, we will literally explode. It will get very, very warm indeed. So I guess the idea here is, can we, instead of growing and doing things in the way we're doing in computing, can we perhaps look at the brain and try to start computing in the way the brain does to try to be a bit more efficient whilst keeping these computing speeds that we're achieving at the moment. So this is indeed neuromorphic computing, the idea to look at the brain to do computing in the same way the brain does, or at least inspired by it. So this is not something new. This has been done for quite some time. Neuromorphic computing systems have been implemented in electronic technologies. So there are different systems. I just brought a few examples here by IBM, True North, or Neurogrid, HiCAN in Heidelberg University, Spinnaker in Manchester University, Loihi more recently by Intel. And these are amazing systems implemented in electronic technologies that are able to emulate thousands, if not tens of thousands or millions of neurons interconnected together. So amazing things. However, they're implemented in electronic systems which have their inherent fundamental limitations, okay? In terms of crosstalk, interference, the length of the communication links that can be implemented in these platforms. And that at the end of the day has a fundamental limit in terms of the maximum available bandwidth, so speeds that can be possible with these systems, and also in their energy consumption. So going forward, it's been suggested in recent times, and this is what we're looking into, that the use of neuromorphic photonic platforms, or going in implementing photonic technologies to development of neuromorphic computing, can go beyond the current state of the art. Okay, so you can see here more or less where the current neuromorphic electronic platforms stand, and by implementing these particular systems on photonic technologies, we can go to higher computational efficiencies, low energy consumption, and higher computational speeds. Okay, because the use of photons have certain advantages. We don't have these limits in interference and crosstalk that perhaps electronic systems suffer from, and we can develop very long communication links with optical fibers or any other platforms. And they are low speed, they have reduced reduced footprints, and they will allow low energy and high speed operation, basically. So there are different approaches out there, but basically in our work, we're using lasers, semiconductor lasers, and we are using the very same devices that are used to transmit internet data traffic over fiber optic networks. So our approach is totally compatible with optical networks, optical communication systems, and data center technologies. And among lasers, we're interested in a specific type, which is called VCSELs. It stands for vertical cavity surface emitting lasers. And these particular devices have the advantage that they are very inexpensive because they can be fabricated and they have vertical emission, so we can test them directly on chip. That reduces dramatically their costs. They have very small footprints, micrometers or lower, and they allow very high speed, and they permit their integration in 2D arrays of devices, which allows for scalability. And these devices are actually ubiquitous in our societies because you can find them nowadays in our mobile phones. They're used for autofocus functionalities, for facial recognition. They are in automotive sensors to do the LiDAR operations and everything that goes into sensing the environment. They are used in supermarket barcode scanners. When you go to Tesco or supermarkets over there in Portugal or elsewhere, just do the checkout, you're using this technology. And in many different real-world, everyday systems. So our research vision is to develop transformative light-enabled laser-based neuromorphic photonic systems for artificial intelligence that are compact, ultra-fast, and low energy. This is where we believe our contribution can be meaningful. So how we're doing this? So basically, we are using this type of devices, VCSELs, at wavelengths of operation directly used in telecom communication systems, so 1300, 1550 nanometers. And we build setups which are used fiber optic elements, so optical fiber systems that you can go and buy, and they're commercially available, and they are widely deployed. And basically, we can use one of our devices here, and we can operate it actually as an artificial photonic neuron, an artificial photonic spiking neuron. We can generate signals from another laser, much as neurons receive signals from neighboring neurons in the brain. And we can encode specific signals in this laser light that we are injecting into our devices. So we can encode signals like this one here, a constant level and certain perturbations, like stimuli that neurons would receive. And we can control how fast these perturbations are in time and how strong they are. However, we are talking about lasers here. We are talking about devices that have sub-nanosecond speed dynamical operation. So our perturbations are no longer in millisecond timescales, but they are in picosecond or nanosecond timescales, so very much faster than actual neurons. And what happens here is that we can encode these perturbations, and the system basically is in equilibrium. And as soon as this perturbation arrives, the device is brought out of equilibrium. It's an excitable system, and indeed it reacts in the same way that a neuron would do, by firing a spike when stimulated. Okay, the difference here is that this spike is just 100 picoseconds or so long, so very, very much faster than biological neuronal spikes. And this map shows basically that if we repeat this process 200 times, so for every single one of these iterations, for every single one of these 200 stimuli arriving into our device, this constant line basically is telling me that we are getting the same spike fired by every single one of the perturbations. So it's something which is reproducible, and it's a reproducible measurement. It's not a one-off. Okay. So the idea here is that we've got these ultra-fast photonic spiking neurons with these laser systems that are very fast and will require low energy for operation. So now that we've got this platform, can we use it to do some spike processing functionalities towards neuromorphic photonic systems with increasing complexity? And this is where we're going. So one of the things that we can do is coincidence detection. So this is a particular operation very useful when you're doing systems for alarm triggering or ultra-fast decision making. So our system is able to integrate multiple inputs from different sources in a way that if you just get a system with a perturbation that is high enough, it will fire a spike, okay? One of these short spikes, 100 picoseconds. But if you send one signal that is not enough to cross the threshold for excitation, the system does not fire a spike at all. If we send multiple signals with certain time delay between them, albeit small, if this time delay is far enough so the energies of the two input signals don't add up together, the system will not fire a spike, as it is in the case indicated here. These two signals are separated by 750 picoseconds, but their combined energy is not enough to go over the threshold, no spike is fired. However, if we reduce the time delay, so less than 500 picoseconds, then their energies add up, their combined energy brings the system over the threshold, and we get a spike being fired, okay? So we get this ability to do this rapid detection of coincident arriving signals, which could come from different sensing elements. We have used this recently also for pattern recognition. So we can put patterns like 4-bit patterns here, for example, and apply a weight matrix and program our system so it only fires a spike upon the arrival of a specific parameter, of one of these specific patterns, in this case, pattern C. So you will see that we put this pattern A, B, C, and D with different combination of bits, but the system is only programmed to fire a pattern when this particular, fire spike when this particular pattern arrives. And these bits, again, this high-speed operation, so these bits are encoded with 80 picosecond pulses. Okay, and the spike fire is like 100 picoseconds long. So just I brought here a confusion matrix just to highlight the fact that we can get this process to work with high efficiency and high accuracy, in the sense that if we want to recognize pattern C, we get that with high fidelity. This is shown by the high values here in this diagonal, basically. This basically means that we are achieving 98 or 97% efficiency in recognizing these patterns. What else? We had also recently been looking to using this particular platform for basic image processing. I think this is particularly important for this the topic of this talk, Edge AI, in which you could imagine systems connected to your mobile phone or to any particular sensing platform, receiving images from the outer world, and you could reduce the dimensionality of the data that you generate in order to transmit that data to a central operating unit further down the line. So one thing that we've done is this edge feature detection by applying different kernel operators. So this is a cross that we fit in, or a Scottish flag with a lot of diagonals over there. And we can do this edge feature detection operation by getting our spike neuron to fire whenever it detects a specific feature, basically. And basically these yellow lines that you see here correspond to one spike being fired by a neuron. So you can clearly see how this system is able to recognize all the edges in the digital images that we're feeding into it. So these images are obviously very basic, but recently we have also get it to work with high complex images as well. So just this horse head image here And you can see how we can get the edge feature information from that type of images as well with these spiking signals, again, operating at sub-nanosecond spiking regimes. What else have we done? So this is slightly off track, but the idea that we can combine multiple of these elements together to do some basic neuronal circuit emulation. And we can combine 3 of these devices to reproduce this basic circuit that is found in the human retina, form of a photoreceptor, a bipolar cell, and a retinal ganglion cell. And that basically connects the light arriving into the eye to the information that is transmitted into the inner brain via the optic nerve. The idea here, again, being this possibility to connect edge systems at the edge, like the eye, okay, with more complex units in the inner brain. And again, we get these particular behaviors reproduced, the depolarization experienced by the photoreceptors, how is that translated to the output of these so-called bipolar cells, and the final spiking regimes delivered by these retinal ganglion cells. And again, let me emphasize the case that this is obviously working at nanosecond, sub-nanosecond speed regimes, so much faster than actually biological systems. And also just to give you a hint of other activities that we are interested at the moment, in addition to these spiking systems towards the spiking neural networks with light-based technologies, we're also working towards the development of recurrent neural networks or reservoir computing systems with lasers. And in particular, we're focusing in a system that is very, very hardware friendly, just using one laser and a delay line. We are building a so-called time delay reservoir. So basically with one nonlinear element, we're using one laser, one of these VCSELs that I'm talking about, and we create a delay line. So we just have a line that feeds back the signal emitted by this laser back into it. And what we do is that we equate time instants within our delay line to virtual nodes, okay? So just by creating this delay line and defining specific instance, we can create a neural network with full recurrent connections, because these nodes are connected between themselves and are connected to neighboring neurons in the system. We can create a neural network with hundreds of nodes or thousands of nodes. So this is very, very hardware friendly indeed. And in this particular system, the connections or the weights between the nodes are fixed, and so are the weights that we're feeding with information into the network. So this particular technique, in addition to being very, very hardware friendly, because it only requires one laser for its implementation, it only requires the training of the output weights. So that is indeed reduces the training and learning consumption as well. So as said, we can build this system using one laser. This is the diagram of the system that we've built, again, using telecom components, things that you can go and buy. Everything is off the shelf at 1550 nanometers, and just a delay line here. And in our system, the delay time is 65 nanoseconds, and we use a time rate of 5 gigasamples per second. That allows us to emulate a network with this simple system using one laser of 325 nodes already. And this particular implementation, it's very good for applications such as prediction tasks, okay? Because this recurrent neural network has memory, is very good at inferring what is going to happen in next values in complex data series. So we have used this particular system for the prediction of next events in chaotic time data series. And basically just here, not getting into much details, but you can see that we get the error in this access and the injection power that we put in, and you can get to see that we are able to predict the next value in a complex data series with very high fidelity for very low values of injected power and in a very hardware-friendly implementation. Another application that we're looking into is the channel equalization task. This is a classification task, ending what happens when you transmit a signal through wireless communication to a phone, for example, and that signal will bounce through different routes and will be distorted, will suffer from noise. So at the end of the day, the specific symbols that you have transmitted will be degraded, and you need to recover that information. And we're able to do that by training this recurrent neural network, just built with one laser. And again, this is the symbol error rate in comparison versus the injected power. And again, you can see that we can get very, very high symbol recognition, so low symbol error recognition with this particular system. So I guess the message to take home is that we believe that photonic technologies can have a big impact on neuromorphic computing systems for ultra-fast artificial intelligence. The idea that we can build artificial photonic neurons and neural networks with lasers, and that will use a spike in processing capabilities to operate, hence reducing operation energy requirements and improving speed. We are working towards photonic spike processing systems with these particular elements, with VCSELs, ubiquitous lasers in our society. And also we can develop photonic reservoir computing systems which emulate themselves with very hardware-friendly systems, full neural networks, able to process complex tasks. And this is the last point, that we are not doing this as an exercise, academic exercise, but we are focusing into functional tasks such as image processing, pattern recognition, time series prediction, channel equalization tasks, and so on. And just to finish, this is obviously not a solo effort, but there's a big team behind this. So this is one of the last pictures that we took in our lab before the pandemic hit. So when we were able to get close together. So these are just a few folk in my lab, but there are many others and people that have already left. And last but not least, obviously the sources of funding, okay, and including the Turing I Fellowship by the UK government. And nothing else, just to reinforce my gratitude for this kind invitation, and I hope it will bring some new ideas to the discussion. Thank you very much indeed.
Thank you very much, Antonio. Very interesting presentation. So I have here a question. So for the functional tasks, for example, image processing, what is the encoding trick that allows us to feed this type of data to such systems?
Okay, so the way we're doing this is that we're obviously encoding the image information into an optical line. So we basically can create these source images ourselves, and we are using arbitrary waveform generators and elements which are called optical modulators, which convert electronic information into the optical line. So we can put a constant light from a laser, and we can put this electronic information in which we are serializing the image information, and we can convert that to the optical line, which goes into our lasers. I don't know if that replies this question, but basically we are getting the image information, which is obviously a two-dimensional information, X and Y. We are serializing it. We convert that into specific pulses, basically, in the electronic domain, and we feed that via an optical modulator into our optical line that gets into our laser. And our laser basically triggers a spike in responses, which depend on the specific features that we will like to basically detect. We can do both things, basically, edge detection and small pattern recognition platforms for more like pooling alternatives as well. And we encode these pulses. So again, we can encode every pixel information in 100 picoseconds or so.
Okay, Antonio, thank you very much once again. So I think there will be time for some more discussion during the panel. So let's move on. So our next speaker is André Lourenço. So André Lourenço is the CEO and the co-founder of CardioID Technologies. So at CardioID Technologies, he is converting ECG biometrics research into an innovative business. He is also an invited professor at Lisbon Superior Engineering Institute, where he lectures information processing and programming. So thank you, André. So the floor is yours. You can present now.
Thank you very much, Luis, and also CTM and the INESC Tech team for the invitation and to remember CardioID for presenting this. It's a pleasure to be here and to present you so what we have been doing in these last couple of years. And so the title of our presentation is Integrating Physiological Monitoring in the Industry, as you said. And so this all began several years ago when I was doing the PhD at Technical, where I was studying pattern recognition, machine learning, in particular devoted to to biological signals and to physiological signals, and its application in the field of biometrics. So there is the possibility of using, as Philippe presented before, several biometric traits for recognizing the humans and so other living beings. And we choose to focus on the ECG since it was a signal that was there and it was possible to acquire in a different way as it was typically done before. And so we started looking at these particularities of the ECG that were not so used to be performed by clinicians. And so what we saw, and it was something that came in research in the beginning of the 2001, 2001, 2002, it was the thing that each art beat was unique from person to person, and it was possible to identify that part of these signals are maintained over time, and it is possible to do biometrics with this. And so this is the base idea of what we are trying to do in terms of identifying the users based on ECG. This is just an example of 2 users, and even by just looking to the pictures, we see that the T is very different from each of the users, and it is almost permanent over time. And this signal is very interesting because it also carries information about the sympathetic part of our autonomic system, and so we can also analyze several psychophysiological status as the drowsiness, as the stress, and so the rhythm is also very important and can be analyzed over time. And so here are some practical examples to show you that this is something that we not only acquire in the lab, but also in the world. And these are some examples of ECGs that we acquired in Ford Motor Company when we installed our apparatus in some of their vehicles. And so, of course, there is a lot of noise, but of course, there is also a lot of information. And so here the challenge is how to get the good ECG from this noise. So as a typical spin-off, we had several papers and a lot of scientific recognition before creating the company, and so the company was born in 2014. Now we are 7 with several interns. Our main place is at CEIA. We have our R&D office in Isel in Lisbon. So we are trying to be present all over Portugal, and so what we are doing is to do context-based physiological computing. So we are connecting biometrics and analysis of the cardiac signals with the context. And with that, we can do biometrics, drowsiness, well-being, human factors engineering. So a lot of products that can be developed. And we structured this in 3 areas. So automotive and the development of edge systems with a lot of edge processing. R&D, where we are doing integration of our technology with several players. And then health and well-being, where we are so integrating this ECG and this PPG processing with health products. And so I will show you several projects related with each of these areas. We have some industrial protection, so patents are important in this for transforming this knowledge and implementing it in the industry, mainly when we are thinking on large scale. And so we have a patent that is already granted. It's like a family of patents already in Portugal, USA, Canada, Japan, and South Korea, and it is still pending on EU. And it has several embodiments that concerned the steering wheel, the tablet, and other possibilities. But all of them are centralized on this. So we think that ECG can be acquired not using electrodes, but using of the person apparatus, like using only the ends as point of contact, and then we can do the processing locally or in the cloud to have indicators related with well-being, biometrics, and then drowsiness or fatigue. And further on, we go for clinical indicators. So we think that there is a world of opportunities for this technology. So the ECG is central on the health and on patient care, but we think that it can be integrated on several other embodiments for control access on computers, on tablets, even on the mobility in cars and other vehicles as motorcycles, in consoles where we can detect the emotions of the person, and for, of course, in gyms and in fitness, where we can, for example, create electronic coaches based on DCG. We can detect where the user is interacting with the machine. And so we created for this a board, an electronic board, where we deployed our sensor and then some of the signal processing and some of the machine learning, and created a lot of interfaces to interact with other providers. The skills that we have required for this and that are part of our portfolio now are cardiac continuous monitoring, heart abnormal activity monitoring, congestive heart failure. So a lot of stuff, of course, related with cardiac topic, cardiac rehabilitation, then ECG and PPZ signal data analysis and acquisition, and the combination with other complementary data sources as inertial data. And for this, in our team and with the people that are working with us, we have several, so it's like a full stack of skills. We have won some awards related with the application of our technology in some use cases, from some municipality pilots that led to the deployment of the technology, to collaborations with the Prevenção Rodoviária Portuguesa and Autoridade Nacional de Segurança Rodoviária, which are the two of the big players related with safety in Portugal, to mobility awards and some other co-creation initiatives. So we tried to put the technology directly in the industry. Here are some of the news that show that, and you can see it on our website, and also some radar of technologies where cardio ID appears related with the automotive industry, and some of the startups that are working with driver monitoring. And so I will present here some projects relating with the industry. One of them is entitled Sensity, and it's a project where we include our steering wheel cover, which is this cardio wheel. It's our first product, which is a steering wheel cover that can be retrofitted on existing vehicles, and that enables the acquisition of ECG when we are interacting with the steering wheel. Then we have also the possibility of monitoring the ECG with smart t-shirts that are more used, and there are several providers. We have also a technology that can be included in a t-shirt, and we have the cardio vest. And then we have the monetization of the other information regarding with what is happening in this case, either in a car, either when the worker is working outside from the car. So monitoring the context with the inertial sensors or with the communication with the car in order to know what is the context where he is operating in that moment. This project can be integrated mainly in contexts where the worker requires a special kind of monitoring, as for example lone workers or workers that work with other cargoes or dangerous situations, and where we can monitor continuously the well-being and trigger events if something happens, and with this we can give the supervisors of the factories and of these dangerous operations indicators that everything is operating as it should be. This can also be used in a perspective of security. So matching safety, that was the first perspective that I gave, with security, because we are monitoring constant the identity of the person with the ECG biometrics. And this can be included on other contexts, and I will show you in the next few slides a big picture of this being included on a mobility scenario. So we have participated in several collaborative projects that helped, starting from a base technology and then create prototypes that were validated and were deployed in the real world. So the Solfi, the Impact Connected Car, and Barraqueiro Transport project were part of this pipeline. We have a collaborative project that integrates INESC tech called Automotives. It stands for Automatic Multimodal Drowsiness Detection for Smart Vehicles. And these are some of the photos of one of the simulators that we created. So we are monitoring not only the ECG, but also actively we are using cameras with near infrared image. So it's not only RGB, but 3D image of the person. And we are also monitoring with a wearable the peripheral signals, and we are combining everything to create models that can be interchanged between person to person and to detect the drowsiness of the driver. This project started a few years ago, and now we are finalizing it with acquiring a lot of data to apply the models that were created. We are also working on a different perspective on a project for predicting the risk of COVID patients, mainly in terms of cardiac signals, and this was a project that started this last year, on the end of this last year, and where we are interacting with Centro Hospitalar da Universidade de Lisboa Central and with Técnico and with ISEL in order to create these models for predicting what is going to happen for COVID patients. And we have a very interesting database now with more than 600 patients that were part of the UCI, so cuidados intensivos, and we are analyzing it, and it's really amazing. So coming from the health and this multimodal processing, we also started doing that with SAIA in a P2020 project, where we included our technology in bikes. The idea was to do processing of non-intrusive and non-collaborative ECG acquired on the hand grips of a bike, mainly focusing on shared mobility. And we created several prototypes and the technology that can be then integrated by the bike manufacturers. The project was called Generation Mobi. And finally, I will just give a little bit more detail about iDreams project, which is a big H2020 project where we are working with so certain partners and several countries, and we are the leaders of the implementation and the technological partners that are implementing the concept. And so the idea is from iDreams, this concept to the industry and what we are doing. And so this project put together our idea of monitoring the context and the physiological signals. And so what we are doing is to monitor not only what the operator is feeling in terms of physiological signals, but also what is happening with the vehicle and what is happening with the context, with cameras. And so with that, we are creating two dimensions, two type of indicators, a coping capacity indicator that shows if the operator is available and is concentrated on the task, and if the vehicle is in conditions to operate. And we have a text complexity measure that gives us an indication what is the complexity of the operation that has to be taken. And with that, we can have a safety tolerance zone estimation, which will give us in real time, and this is very important, in real time what smart ADAS can trigger to the operator. And then we can give in a post-trip momentum. So after the trip, several tips and several and the summary of what happens in the past trips and how can the driver improve. This is being done with the University of Hasselt, with TUM, so Technical University of Munich, Delft, Loughborough, Athens, and then with some other companies. And so this is the framework that we are implementing. So we are combining a multimodal environment, and I think this is the more important part. So not looking only to the physiological part, not looking only to the vehicle, neither to the context. We are combining everything, and with that we are trying to have a better image of what is really happening in each situation. So we are integrating, for example, traffic information, weather information. The models can also have the topography of the place where we are driving. We can have, for example, statistics and black spots over the geographical informations to have like a prior over each of the places where the driver will go. And that can be integrated in real time with the driver capability and with the vehicle capability. And so we can trigger actions that are dependent on all of these factors. And this is all done in an edge computer device that is called Cardio Gateway. So that was something that we also created. So our second product, which is an edge computer device that has the capability of acquiring information from CAN bus, from smartphones, from several cameras, receiving information from physiological sensors, and then combine everything. It has the GPS and 4G capability or 5G capability. It is really easy to upgrade it to 5G or 6G. And we are in this precise moment starting the validation of this in several countries. As you see, we are going to have several countries with a lot of vehicles and different modes. So this will be validated not only for light vehicles, but also for trucks, transportation, passenger transportation vehicles, and also trams. And so it's a big pool of data, and it's a big challenge. So this is the unit, which is closely related with the topic of this panel. So why doing edge computing on a situation, and in this case we think it was impossible to do it in a different way, because it is dealing with human machine interface, and so we need to have actions that are triggered in that time. We need real time, and we don't. So even if the intelligence is on the edge, as Jaime told us in the beginning of the session, we need that the latency is very, very short. Let's discuss, of course, it on the panel, but I think in this case, of course, there could be other paradigms, but I think the edge computing paradigm is very well suited. The requirements for the product were to integrate several interfaces and to have the connection with a lot of standards that are already in the vehicles, as the FMS, so stands for Fleet Management Standard, and our computational capability in this case is a quad-core Cortex A72 with the possibility of including a TensorFlow processing unit if we require to do some kind of video processing on the edge. And so for the physiological.
Yes. Could you try to speed up so we can?
Yes, I'm finishing, Luis. Sorry. And so the physiological data is being acquired by cardio wheel or by the wearable, and so it is a very interesting scenario. These are the test vehicles that we are where you can see the technology, and that's it. So thank you for the time, and sorry for the few minutes that I have surpassed the time.
Okay. Thank you very much, Andre. Thank you. So are there any questions, please? Okay, so I don't see any in the chat. So maybe I'll bring a question. So is there, what do you think is the role of the 6G and this movement towards lower latency communications? How is it important to enable these applications that you were talking about right now?
So I think it's fundamental to have this low latency if we want to move the processing from the vehicles to a centralized or to a near the edge scenario, and so I think it can be an option, but of course then it depends on the costs, Luis, and this is also something that I want to bring to the panel, because the clients don't want to have to pay a lot for this kind of technology, and so this is also something that we need to discuss. It's very interesting to have operators, but if the costs are going to be very high, I think that it's not going to be possible. But let's discuss in the end.
Okay. Thank you very much. Okay, so we'll move on to the next speaker. So I see that Mehdi Benis is already in presenter mode. So let me introduce Mehdi Benis. Is an associate professor at the Center for Wireless Communications, University of Oulu, Finland, Academy of Finland Research Fellow, and Head of Intelligent Connectivity and Network Systems Group. So his main research interests are in the radio resource management, heterogeneous networks, game theory, and distributed machine learning in 5G networks and beyond. So Mehdi, it is my pleasure to give you the floor to provide.
Thank you very much, Luis. So I hope you can hear me very well and see my slides.
Perfect.
First,
yes.
Let me first thank you for inviting me to attend this very interesting workshop. So as the title says, I'm going to talk about edge AI over wireless. This includes some of the current research we are doing currently in my group, but also going all around the community. And I'll conclude with one slide, basically, where the future of where edge AI should go. All right. So let me get started. So the proliferation of intelligent devices and mission critical applications at the edge, such as virtual reality, autonomous driving, and so on, cannot be operated with best effort and machine learning and best effort machine learning. On one hand, these devices need to train their models by essentially communicating with other devices, either directly or via federating server. And there are a number of constraints. Typically, we are in the small data regime, right? We are no longer in the big data setting of the cloud. We have constraints in terms of memory, storage, compute, and the data is typically non-IIG, right? On the other hand, these devices need to learn also how to communicate in an ultra and reliable and low latency manner. And there are a number of constraints such as channel dynamics, network dynamics, limited communication, and so on. So this learning to communicate while communicating learn requires a novel machine learning and communication co-design, giving rise to a number of fundamental challenges. So some of them are listed here. How do you do communication efficient training, fast training, reliable training? How do you do fast and low latency, energy efficient inference at the edge? And also, if you push that to the realm of reinforcement learning or control in general, how can you do, again, fully distributed, privacy preserving control while taking into account all these constraints? So these slides should be known to some of you. Essentially, this is the departure from the cloud-based centralized AI, where essentially raw data was transmitted from the device all the way to the cloud for training, inference, and so on. So this was fine for some time, I guess, but we all know that this is violating privacy. It's certainly not good for low latency communication, and certainly just wastes bandwidth. So this is why we have seen this kind of upsurge or groundswell interest in federated learning, coined by Google in 2017, quite counterintuitively, right? So Google is all about collecting your data, but they propose this nice idea of federated learning, where now, instead of transmitting the raw data, you transmit a model, right, of your data to the cloud, and then the cloud will just do some kind of averaging or computing over this data, and then it transmits back these models all the way to the device. So this is great, actually, because this is privacy preserving, it's bandwidth efficient, and also you still can use the cloud, but in a different manner. Here, essentially just averaging these model updates. And of course, you could get rid of Google or maybe the server and do this in a fully distributed manner. This is called swarm AI, but you can think of it also as fully distributed AI over wireless. And this actually is better than federated learning in the sense that it allows you to scale completely throughout the network. Okay. So here is one slide which will guide me to really present to you some of the family of techniques that we know in the literature. So one of them is actually referred to as model parameter exchange. This is where federated learning falls. So essentially, you have a bunch of devices, a helper or a server, and you want to train a model in a fully distributed, privacy preserving manner. Okay, and you have a bunch of family of algorithms, as I said. One of them is federated learning, but of course there are many others. So I'll present to you briefly what we mean by group ADMM. Essentially, the idea of going toward serverless federated learning. In the middle here, you have what we call model output exchange. So here, unlike the case of federated learning where you transmit the entire model parameter, here you only transmit what we call the logit or the model output to the server, which again does some sort of averaging. So there's a technique called federated distillation, which I'll very briefly mention to you. And last but not least, there's a very nice trend of research, which is not really under the limelight as federated learning and others. Essentially here is to train not based on the raw data, but essentially on a surrogate or a summary of this data. And this is not something I'm gonna cover today, but just for your interest. Okay, so let's start. So here, essentially what you see here, this was the first application of federated learning in wireless communication. And essentially what we focus on here is the use case, 5G use case of ultra reliable vehicular communication, where you have a bunch of vehicles here. I hope you can see my cursor here, a bunch of vehicles which want to train a model. So in this case, the model is essentially a tail distribution of the delay profile. So it could be the low latency transmission, if you want to think about it this way. And here the problem essentially is this distribution is not known to the vehicles, right? So they need to learn it on the fly. So essentially this is where we use the technique of federated learning, where now the vehicle will basically, based on the local data that they have, build a model, right? And then transmit this to the roadside unit. And the roadside unit, in this case, just averages these models and then broadcasts them back to the vehicle, so that the vehicle now has in its possession this distribution to then act upon it, meaning transmit its power or associate to a different vehicle or any type of system design you want to think of. Okay, so we kind of cast this in a very nice problem, because we also had to look at the long tail problem. So we used some techniques from mathematical finance, and in this case it was extreme value theory. I'm not going to bore you here with the mathematics, but I just want to maybe point you to the result here, basically comparing the centralized case, which is here in circle, with the extreme FL, so extreme value theory based federated learning, comparing both the communication payload, right, here in blue, and this is the probability of reliability, and this is the total number of vehicles. So as you can see, essentially that the extreme value or federated learning approach achieve the same reliability as the centralized approach, right? While communicating much less. So essentially, you get a free meal approach here, free meal result. Essentially, that of course, since I'm not transmitting the raw data, I'm transmitting the model. So essentially, I have a smaller payload. But you can of course extrapolate this to autonomous vehicles, where now you have actually high definition cameras, so the gain will be even more pronounced. Okay. Now, as I said to you, now another family of results essentially is try to get rid of the server-based federated learning approach. So remember, federated learning have a server and a bunch of devices. Here, what we want to do is essentially move to a totally distributed setting. So here, what I'm showing you here, this is a fully distributed setting. Think of it as a random deployment of edge devices. This could be sensors, cameras, vehicles, right? And now we want to essentially do the same thing, essentially train a model, right, across these devices. But now, instead of transmitting from all the workers or devices of the server, here what we will be doing is we will basically partition this network in terms of two groups, and every device will be just basically communicating with its immediate neighbor based on some criteria, essentially based on the signal to noise ratio, based on the location, based on maybe informative sample or informative model. And as a result, you will be able to completely propagate this model all the way from, say, this node here at the edge towards the yellow one here. Essentially doing federated learning, but again, in a fully distributed manner, okay? So here, just to show you some results, this is for linear regression as an example here, compare essentially, this is an objective error here as a number of iterations, comparing the proposed approach, by the way, it's called group alternating direction method of multiplier, versus a number of baseline here, so gradient descent, stochastic gradient descent, and a number of baselines, lazily aggregated descent. But really, without paying much attention to these baselines, what you can see here is a dramatic, reduction in terms of error due to the fact simply that you are communicating, locally or in proximity. This is basically the take-home message. You could also have a much lower cumulative communication cost, of course, again, because you transmit much less towards neighboring devices, and you can reach the same accuracy as if you had a fully, say, centralized setting. Now, while this was actually for full model precision, the natural question in this type of work is, what if we now quantize the model? Instead of transmitting a 32-bit model, can I actually try to, reduce it to, say, 2 bits or 4 bits? And see how much accuracy drop you can incur. This is essentially what we did here. So we try to map this again in a kind of stochastic optimization framework, try to find what is the range of my quantizer, and also pay attention to the fact that you don't want the error to accumulate. So typically when you quantize, there is an error, of course, which accumulates and may actually hinder conversions. So we need to take care a bit of that, but that's not an issue. We can actually even prove that the algorithm can converge. And what you can see on the right-hand side, essentially, again, this is the objective loss or test accuracy versus the total number of transmitted bits for the quantized model, right, versus the non-quantized model, and a bunch of other baselines. And you can see again here that you can get a free meal in terms of not paying any price in terms of accuracy, but significantly less a payload or faster convergence, in other words. Okay. Another type of very interesting work is now when you talk about, because a lot of people talk about co-designing, machine learning, and communication, but by that, they don't really do the job, or they don't pay a service to the area, in the sense that what we really mean by co-designing machine learning and communication, essentially, you need to contrast two designs. So we need to understand that there is a digital communication-based federated learning. So here, again, you have your devices, your worker, your helper, sorry, and essentially, when you say that you're transmitting a model from the edge device to the server, you're implicitly saying that you have an orthogonal bandwidth for you. And we know that that's not how it works in practice, right? And we also know that if you have so many devices here, which is the assumption of federated learning anyways, this is not scalable, right? This is definitely not scalable. So now what if you could solve this issue by maybe trying to orthogonalize the transmissions, but you would run out of spectrum quickly. The other paradigm is you flip it a little bit upside down, and now, since we are not interested in decoding the individual models, remember in federated learning, what you want to decode is the average model. So essentially here, we can leverage principles from analog communication, essentially leveraging the superposition nature of the wireless channel to aggregate the models at the server, and of course they will be perturbed by some noise and some fading, but still you could actually decode this. The nice feature here is essentially that you can scale much better than the digital approach, and it's still privacy, of course, preserving, and actually the performance improves with adding more devices, whereas here the performance decreases, right? So essentially, this is one of the New York papers last year. We compared essentially in terms of communication efficiency and energy efficiency of our approach here. Again, is the one here in red for analog SVADMM with a bunch of digital, of course, baselines. And you can see here that you can achieve much faster convergence rate compared to the digital approach. You could even push it to the fact that now we try to see now, what if I give 10 times more or 100 times more bandwidth to the digital baseline and see whether it can really outperform. And you can see that it starts to, when you multiply by 2 orders of magnitude. So it's a very, very kind of nice paradigm to be leveraged. Here, this is the same thing for energy efficiency. So it's actually even better for low power sensors. This is much better actually than using the digital approach. Okay, now moving on to this other technique, again, called federated distillation, which is a very nice in the sense that now, as I told you before, what you want to be transmitting is the logit, or for those who don't know what a logit, here you have an input. This is a neural network, and this is essentially the distribution or continuous value that you, before you feed it to your ReLU or Max or any other sigmoid, right? You want to train your model based on this kind of knowledge. This is where the knowledge distillation paradigm comes in, and essentially this is what every device does: transmit the logit to the server, aggregate, and then you try to distill this knowledge from the teacher, because now the teacher is all this bunch of devices around you. Distill this knowledge to the device and help him train better and achieve a better accuracy than if he was not, of course, training with them. You could write this mathematically for those who are interested in this. It boils down to adding kind of an error, which is a prediction difference between the teacher and the student. So if you are closer to the prediction of the teacher, you don't have to do anything. But if the gap is bigger, then you have to add it as a regularizer. We compare this to federated learning here. Our approach here is federated distillation. This is the sum communication cost, and this is the number of devices. So you can see here that we have a significant reduction in communication, actually payload, which is great. There is a downside to this technique, essentially, that you pay a little bit in terms of accuracy, right here. If you compare, this is again federated learning, federated distillation for the non-AID setting, which is really the case where we are dealing with here. But you could remedy to this by other techniques, such as training a generative adversarial network to essentially help you deal with this lack of samples. I mean, there are some other techniques that can address this issue. Another technique, actually, which is now gaining attraction in the edge AI community, which is also very kind of engineering focused, is the idea of split learning. Okay, so I don't know how many of you have heard about this, but essentially think of it as this setting. Here we are interested in a channel blockage prediction in a millimeter wave setting. As you know, in millimeter wave, one of the problems is, if the channel is blocked, that means that, I don't know, it's essentially it may have some bad performance in terms of its safety application, or autonomous vehicle loses a connection. We really want to predict the channel when it will be blocked before it actually happens. So here what we did, we tried to combine or do some kind of multimodal prediction, essentially 2 modalities. One is RF modality, right? This is what we measure in terms of received signal. And another modality, which is rich and free. And this is provided to us by a camera. So think of it, you have a camera, which essentially is capturing here a pedestrian, or think of it as an environment, and try to essentially transmit these output features all the way to the base station, which could be here another vehicle, could be the roadside unit, could be a server, and then likewise the base station, which also has RF signals, which also extract some knowledge and feed it to another neural network here, and then you can map this to say a convolutional LSTM, and they help you predict. So essentially, we try to see how we can transfer these 2 modalities to help us predict better. And that's actually what we did here. This is what you see on the left. This is the test performance in terms of root mean square error. This is the communication cost, essentially to tell us how much compression should the camera do here before transmitting this tensor forward to the server, right? So of course there's an accuracy communication trade-off here. But what's interesting to see essentially here, for those who a bit are sensitive when they hear camera, because of privacy issues, we were trying to play a little bit with the filter dimensions of the, you see here the camera, this is the raw images. If you play with the filter, you can actually go all the way to 1 pixel, which is actually exemplified here by 40 by 40. And interestingly, even with 1 pixel information, if you combine this with the received power only, right, you can actually outperform even the received power based only prediction. So of course, then if you have more, images and you improve the resolution here, you could obviously outperform it significantly. So this is a nice both theoretical and also kind of application. I mean, there are a lot of works that picked up this work now and try to extend it further towards distributed cameras, towards now even trying to interpolate here in the representational space, right? Instead of interpolating in the raw data space. This is a kind of fertile area of research. All right, and now, of course, maybe what people are waiting for, I just have one slide essentially to tell you what's next, right? So Edge AI is really hot. It's one of the key enablers of 6G and beyond 5G, but we really need to pay attention because there is a fundamental problem, and I'll try to motivate it to you here. So one of the limitations of all this research carried today, number one, I mean, here's a bullet point for you, but one of them is our obsession with accuracy. But we shouldn't forget that there are other aspects such as energy, of course, it has been touched on earlier, robustness, fairness, interpretability, and so on and so forth. Right? So we all talk about sustainability. Well, if you just apply vanilla federated learning, that's basically not sustainable. Now, of course, issues of machine learning on its own, right? Lack of robustness, brittleness, poor generalization, right? These are current themes that are not even understood in the machine learning community, let alone the fact that if you want to apply it in a 6G setting and try to integrate it with communication, this is something we have to be a bit careful with. And also the fact that federated learning essentially is really one step, or I'll call it step 0 actually, or step 1 of what a brain does, right? We all, I mean, some very nice talks about alluding to the brain. Essentially, what we are currently experts in today is just, curve fitting, right? We are basically learning correlations, patterns based on, okay, maybe small data, big data, and so on and so forth. But of course, the human beings are better than that, right? We have other cognitive tasks that allow us to do reasoning. I can reason based on, in a totally new environment, and I can do that on the fly, not without being trained in it, right? Extrapolation, these are new problems which we have to look into because right now we are only doing interpolation, right? Curve fitting. Imagination, we need to be able to look into causality around the what if question, counterfactual reasoning. These are all really important ingredients. And here on the right hand side, because this is a kind of a research area in my group now for a year or so, we need to come up with new desiderata for representations. So of course, in federated learning, we already do, we learn a model, which is a representation of the data, and that's the representation you transmit to the server, right? But we need more. We need more ingredients. We need to be able to learn a representation which are sufficient and minimal. This is not so novel, essentially, because when you compress a model, you're actually satisfying number 2, but we need to look at invariance. Can we learn symmetries in our model, right? Because there's a lot of redundant information. If we try to really use coarse training and learn exactly what will be more important to carry a task, that's very important. Invariance, 3, disentangle, we should be able to disentangle, say, the raw data or raw images we have in terms of objects and try to reason over these relations, attributes, right? And try to reason beyond what we see in our perceptual system. Number 5, of course, causality. Causality, 2021 should be the year of causality. Essentially, I mean, we already see today, I mean, you can run some tests and you can play a little bit, with learning, correlations. As soon as you add noise, it does fails, right? Because essentially you're not learning any, in any robust model. So robustness and causality actually go hand in hand. And now the new objective that I am proposing to the entire research community essentially is to start to learn new representations which are semantic and fulfilling basically this 1 to 5 desiderata to be able to do, X. So what is X here? X could be model training, could be inference, could be control, could be reasoning, could be even communication, right? This is actually how 6G will be. And if we really manage to do that, then the nice benefits are that we'll be able to transmit much less data. speaking of sustainability, more reliability, more energy efficiency, of course, much better than today, sample efficiency, and true intelligence, because as you may have realized, this word of, intelligent communication is being thrown a bit abused sometimes, because essentially, as you can see, we are really at the very beginning of what intelligent communication is. So with this, I thank you very much, and happy to maybe answer some questions.
Thank you very much, Mehdi. So I open the floor for questions from the audience.
Great. Let me see.
Anyone? Okay, so maybe I'll bring a question. In this scenario of edge intelligence, imagine that you have nodes with very low power capability, like in the scenario of UAVs. Is this a blockage, a great limitation, because then you will need to train or make learning happening in the edge, but you don't have so much resources in terms of energy consumption? How can you handle this issue?
So very good question. So it depends. So now if we take the use case of drones, and we've done some work on that, you need to be very careful, because you're not going to be train a model, in the real world. What you have to do is essentially train it in a simulator. And because you need to cover all these edge cases, which obviously if you don't say explore in simulator and just deploy it in the real world, is catastrophic, right? So the current scenarios we see today are, training over MNIST data sets. I call them cats and dogs. This is a data set we have from machine learning community. But once you move to the real world, right, it's autonomous vehicles, that training has to be complemented with simulators. Otherwise, it cannot be deployed in the real world. So now in our specific scenario here of millimeter wave, we actually even did a demo here. This is not very safety critical, right? Here we just have a pedestrian actually, which is walking, right? And you have a camera, which is trying to model his trajectory so as to maybe, in that case, it's a mobility management, it's a handover. So you want to hand him over before the signal drops, right? So you want to reassociate him to, say, a different base station. So it's not really a mission critical application. If it was for a drone or autonomous vehicle, we need to be more cautious. Yeah, sure. Okay. And also, maybe I should add now because I try to stress a bit this long tail problem. So the long tail problem essentially, which is the more difficult one, because you don't have enough data. So you're not going to tell the robot, okay, let's explore the environment and learn this data. No. First of all, maybe it's not possible. Maybe it's not good for safety, obviously. But sometimes, even if I give you 1 billion points, it's not enough. Because essentially you're not learning the causal knowledge or the data generating process of that particular phenomenon. That's why causality here should be added on top of the kind of discriminative, right, approaches we use.
Thank you very much. Thank you very much. So we have to move on. There is one more question in the chat that I encourage you to respond in the chat.
I'll reply to it right now. Okay.
Yes. So let's move on to the next presenter is John Soldatus. So John Soldatus is currently honorary research fellow at the University of Glasgow, UK, and senior R&D consultant innovation delivery specialist with Intersoft International. He has significant experience in working closely with large multinational industries while being scientific advisor to high-tech startup enterprises. He is an expert in Internet of Things and artificial intelligence with experience in Industry 4.0, finance and healthcare applications. So please, John, the floor is yours. Thank you.
Thank you, Lou. Thank you very much, Luis. Thank you for having me here. Thank you for the invitation to INESC. I hope you can hear me right and you can see my slides.
Perfect. Yes.
Very good. So yeah, I'll try to continue from the previous presentations, talking about the issue of edge AI. Well, here I'm Intersoft, just to say a few things about us. We are a multinational firm with presence in 13 countries. Our headquarters are in Luxembourg. We have very big offices in Brussels also and Athens, Greece. and of course, we have a long tradition in delivery and working with the institutions. And I am from the Research and Innovation Delivery Department. And there we are running a lot of research projects, including these types of EU-funded projects like Horizon 2020. So I would like to continue from the previous discussion on the edge computing and edge AI topic. This is not a new topic, but it's actually a very hot, a very topical discussion. Earlier this month, the previous month, I attended two major events in our community, Hanover Messe, and also IIoT, Industrial Internet of Things World. And this was a major topic because it turns out that a lot of data, Gartner predicts 50% of the data by 2023 will be processed at the edge of the network and not in the cloud as we thought a few years ago. And in my view, the reason there is so much discussion about edge computing is because nowadays we have different ways to implement an edge computing concept or an edge cloud computing concept. In the previous presentation, we saw a lot of things about federated machine learning, which is one of the options you have nowadays, but I'll try to delve into some more details on other approaches, starting by saying that at least for industrial applications, edge computing is not new, and it's actually part of the industrial internet reference architectures. Most of the standard-based models like OpenFog reference architecture or reference architecture of Industrial Internet Consortium, if you read these documents, you will see that they propose in the implementation of a cloud edge implementation. However, they don't give you the details of how you can do it. And you have different ways to do it. And here is why we talk about cloud, edge, and far edge. And as the previous colleague was talking about, there are some trade-offs to resolve here. And this defines what is the deployment configuration or the deployment paradigm that you are going to dispose with. So if data points availability is a concern, because let's take an industrial application, predictive maintenance, you need sometimes you need good data points in order to train a model that can accurately predict remaining useful life, for example, then you are leaning towards the cloud. Whereas if your goal is to have energy power efficient operations, or in some industries, data protection, data privacy is most important, then you are leaning towards the edge. And here my definition of edge is the so-called local clouds or fog computing, IoT gateways. But we nowadays talk also about the far edge or AIoT, which means running machine learning within embedded devices or even within microcontrollers. So this is a trade-off game, and you need to agree on what is your goal. Is it real-time performance and field operations, real-time actuation and control? Is it power efficiency? Is it data privacy or data points availability? And then you need to resolve the trade-offs. Now, I put this in a context, of an Industry 4.0 use case, which is, probably one of the most popular industrial use cases. So intelligent asset management, predictive maintenance, or in the broader sense, quality management of products and parts. So you've got good reasons to do the remaining useful life calculation in the cloud, because that's how you're going to build an accurate model. However, if you want to do it fast because you want to implement, for example, some reactive strategy, if something doesn't go very well, in addition to your predictive strategy, then you are likely to be doing this at the edge and at the far edge. So this is these are real problems, and these are, real use cases and real concerns that you might have, and these here come the solutions that help you solve it. Also, we talked about different types of learning, and I want to make a point here that, there are very many good benefits of running machine learning directly on an Internet of Things device or even on a microcontroller. The problem is that we don't usually have as many data or as good data we need to train such a model. But here there are other good things emerging in the AI space, like, for example, transfer learning, which means that you can start with a model on the edge and then use this data to train a model to enhance actually the data you have in another space. And in this way, you don't start from scratch when training a model in a setting. You leverage data that you've got already. So one of the things we are looking at my group recently, this is the last year, is TinyML. So it turns out that you can run machine learning, even deep neural networks, on microcontrollers. And you can get huge benefits because there you don't even have to worry about the bandwidth or the connectivity at all, because you can directly run the insights on the microcontroller. This is what I call far edge. And of course, it is much more power efficient if you can make it work, and you can exploit even more data than ever before, because you don't have the overhead of transmitting the data to a local cloud or to a cloud. And this is becoming real in the last year. So here are some boards that, even if you are a researcher or a developer, you can start experimenting. So very cheap boards like Arduino Nano 33BLE that you can take, and you can have a very nice pipeline of tools, which are, the usual tools we use for embedded programming. So like Arduino IDE and machine learning, like Python, TensorFlow. The difference being Keras, the difference being that here you can use TensorFlow like micro. So the idea is that you train the model with many data points in your cluster, and then you shrink the model and you deploy it on a microcontroller with the lowest possible footprint. This is the direction we are looking. Of course, we have done over the years, we have a platform, we call it a Datacrop, and you can use it to gather data from the field and deploy functionalities either at the edge or route this data in the cloud and have this cloud edge interplay. So typically, we want to transmit to the cloud data points that are of interest because we want to economize on bandwidth and storage. And one of the benefits of our platform here is that it is, I would call it programmable or configurable. So you can build, almost zero programming use cases here by configuring your data sources, the routing of your data across different producers and consumers, but even your analytics can be configurable here. And we have deployed our homegrown at Intrasoft machine learning framework, which we call it QARMA. QARMA stands for Quantitative Associations Rule Mining. So it's a rule mining approach that mines large data set in order to find rules that hold with high confidence. Yes, on the one hand, this outperforms, all the conventional, usual frameworks and algorithms that people use for predicting analytics, like, LSTM or other types of recurrent neural networks. But most important, because this was raised in the previous talk, and this is very important also research topic for now, but also for the future, because the outcome of the rules mining approach are rules, it is a white glass model, so it is explainable, it is interpretable. And this is very, very useful because in the industry, we want to tell the plant manager and even the shop floor engineer why the robot or why the machine learning system is producing a certain recommendation or is guiding towards a certain results. Now, earlier on I said that there are many ways to implement edge computing. So I talked about local clouds, fog computing, far edge, and earlier we've seen federated learning. Another edge computing approach we have tried, and I think that in the future it could play some role, is based on distributed ledger technologies, what most people know as blockchain. Okay. However, these are permission blockchains, not public blockchains, which can have much higher performance. Still not enough for some applications, but we have benchmarked, for example, permission blockchains, and they can support some thousands transactions per second. So what we do here, we went on an industrial architecture, and over the edge layer or the edge tier, we introduced a ledger tier. So we introduced a blockchain infrastructure, which you can use for different purposes, like, for example, data provenance, which is very important in the industry because data are not always reliable. So you can have, by writing it on the blockchain, which has these anti-tampering properties, you can have very good data provenance and data traceability, but also algorithmic traceability, because algorithms can also be susceptible to cybersecurity attacks like poisoning or evasion attacks and so on. So you can write this on a blockchain and have an extra layer of security and anti-tampering properties and trust, but also you can use it in order to configure the way your analytics will operate at the edge, or the real-time automation operations you would like to perform at the edge. So that was one approach, and we tested it in different factories. Like here you see a sorter that is putting different types of products in different bays, and we use it to run a digital twin that could ahead of time simulate and estimate what is the best possible way to place the products that are coming in a conveyor in the different bays. I would like to, having said all that, I would like to end up, although I'm not working, on at the network layer, but because this is a 6G workshop, I think it's very important to underline why 5G will be very important on this story. First of all, for some applications like autonomous driving, distributed AI, previously we talked about drones and so on, then 4G is not enough because we want lower latency and we want to be able to operate in a device-saturated environment. However, for our applications, we see a very strong value proposition in this private 5G space and the ability to develop, customized software-defined networks. So effectively through slicing and network function virtualization, you would like to customize the network that is most appropriate for your factory or plant or other industrial deployment. And there is where 5G and of course 6G, which is mandated to provide this ultra low latency. Of course, we expected to see a huge improvement by 5G becoming mainstream there. Already is going to play a new role to enable these applications, especially applications that are involved real-time automation or that they are extremely data intensive, like I would call them, big data applications. I think the holy grail of all these is probably the autonomous driving. If we think that an autonomous car will have to take 10 decisions per second and be able to see all the driving context, running tens of deep learning algorithms in order to be able to see reliably the road, then we understand the merit of the emerging network. So that's all from my side. And of course, I'm happy to contribute to the future research agenda with some other topics, like, for example, yes, explainable artificial intelligence and interpretable artificial intelligence is going to be a big theme in the years to come, no matter at which layer you are seeing this. So that's, Luis, all from my side. Yeah, maybe I would conclude. I think I've already concluded. So there is not a silver bullet here, a one-size-fits-all approach. Actually, what we need is an edge operating system, right? That you pick up the best deployment configuration depending on your latency, security, data intensity, decentralization, security, robustness requirements. A lot of trade-offs there. So you can't have a single solution. Also talking about future research, and I think for the sake of avoiding fragmentation as Europeans, right, in the European Union, I think, yeah, all institutions, all us that we are working on research, we need to keep an eye on developments in the industrial data spaces, but also more recently on the Gaia X initiative. Each a politically driven initiative, but it's going to be also, in my view, a good placeholder, a good repository, a good catalog for a lot of the applied research that we produce in different institutions around Europe. So that's all from my side. I'm happy to take any questions now or later in the panel.
Yes, thank you, John. So I have here a question for you. So what is your vision for the AI/data regulation and its interactions with academia, research, industry, society?
Well, that's a, sorry, may I see the question, right, Maury? I think, you know, it's, I think there are different ways. I mean, maybe this question relates to what happened 2 weeks ago, right? Because 2 weeks ago, we had the release from the European Parliament of the AI regulation, right? And as Europeans, we are the pioneers in regulating the AI, although we don't have the best AI, right, in the world, right? I think, you know, here we need to maintain a trade-off. Certainly we need regulation, because some of the AI applications are not just about, I mean, the risk or the stakes are not just about financial loss, right? I mean, autonomous driving can have life-threatening implications, right? Or even industrial robots and so on. So certainly some regulation will be required. And, you know, as a European citizen, I would say that, okay, it is great that we are pioneers in protecting our citizens and protecting ourselves with good regulation. On the other hand, as an innovator, I would say that you know, we should maintain some good balance so that we don't limit innovation, right? So we don't. I mean, we don't. We have to steer people in producing intelligent things and producing disruptive things, right? Not steering, you know, young people and young innovators and young researchers on, you know, writing papers about regulation and preparing, you know, regulatory frameworks and so on. So we need to have a good balance. As a citizen, I'm enthusiastic about AI regulation and Europe being pioneer about it. As an innovator or with a more entrepreneurial spirit, I'm saying that, okay, let's not be afraid of it before we create it, and let's maintain a good balance.
Okay, thank you very much, John. Sorry for the delay in general, that we have been delaying a little bit in every presentation. So it's time to move on to the panel discussion. So this panel will be moderated by Professor Manuel Ricardo. So Professor Manuel Ricardo is a full professor at the Faculty of Engineering of the University of Porto, where he teaches courses on computer networks and wireless networks. At INESC, he is director and leads the research cluster on network intelligence systems. His research interests include radio resource management, network congestion control, wireless networks, quality of service, and performance evaluation. So thank you very much, Manuel, for accepting to moderate this panel. So now the floor is yours.
Okay, thank you, Luis. Good afternoon to everyone. So we are a little bit delayed. Can we count with 45 minutes for the discussion, or shall we reduce?
Well, I think we can try to go for 40 minutes or something like that. So
Okay.
By 6 p.m.
So first of all, I would like to thank the members of this panel, António Hurtado, André Lourenço, Mehdi Benis, and John Soldados. It is a pleasure to have you here. And I enjoyed very much your presentations. You gave us some new visions and very interesting, let me say, food for our discussion. I have prepared some open questions for which we would like to have your views. So I could start with the first one. And I will keep these questions, as I said, open and generic, so that, let me say, the people that is attending the workshop can be aware and can be involved in the answers. So my first point or question will be the following. Our center, the Center for Telecommunications and Multimedia, it is involved on some areas of research that are organized as in communication stack. That is, at physical layer, we work on antennas, radio, and electronics. Then we have a group that works on networking, and mainly on networking over wireless links. And often this research is associated to drones. Then we have a multimedia group that is involved on multimedia applications and also communications for multimedia. And then a group which is very much associated to pattern recognition, machine learning, and with their results applied to, let me say, to vision and audio computing. In which way do you believe that we could take advantage of edge intelligence in order to better integrate this diverse activity, or in alternative to jointly optimize our system consisting of these multiple areas of research? Maybe you could go through the same order that you have used for presentations, António, André, Mehdi, and John. And you don't have to answer the question if you don't feel comfortable with the question, but we'd like to listen to your opinion. So maybe António could start.
Yeah, thank you very much. So obviously, I'm a photonics researcher, so my work is more related to the hardware side of things and the optoelectronic and the things that were presented about neuromorphic computing as well. So I think there is a lot of potential for bringing together photonics and electronics, and these are going to be directly coupled to edge systems, because at the end of the day, both photonic systems implemented either with lasers or LEDs or other technologies, photodetectors, are going to be driving the sensing data that this has to be processed down the line. So in my view, there is great potential for incorporating light technologies into AI and certainly to edge systems, from both perspectives of reducing the amount of data that is transmitted to a central network, but also to do some pre-processing in a way inspired by what the retina does. No, that's exactly what the retina does in our eye. Basically, it gets the input signal from the outer world, and when it's transmitted back to the brain is something really much smaller. The data transmission is highly reduced. So from the perspective of what the different areas are in the institute, you covered many different aspects, and all of them are to be integrated together. But I think there is huge potential in hardware developments in photonics for computing and for artificial intelligence. Yeah.
Thank you very much, António. André, would you like to help us on that problem?
So I think all the areas are very important by per se, but the relations that come from connecting them are more important. So, for example, in the projects that we are working with, so in this driver monitoring with edge and real-time actions, we are connected with a lot of network problems, a lot with edge processing that is required. But of course, then we need also to transfer the data to the cloud to have the models learning in a more sophisticated and complex environment, as was referred by the rest of the speakers. So I think the traditional telecom model still is in a sense adequate for the challenges that we have. But of course, I think the researchers are more traveling from one area to the other and speaking more with each other.
Thank you very much. Maybe.
Yeah, maybe I
Would you
can
like
add
to
on
help
that.
us?
Yeah, so I mean, I agree with everything that has been said, because essentially, I mean, edge AI nowadays means, I mean, you can equate it to 6G, but of course, the way I see it is more of an ecosystem, right? So you need the hardware, I will just mention, very important, co-designing the hardware and the machine learning. Communication, it depends, because now what we see with the students here, at least, is the traditional communication centric model is not very attractive anymore to students. So of course, this is because of the machine learning era. But to me personally, I still see a huge benefit from when you talk about decentralizing machine learning. Communication is actually essential. So I still see our relevance in that domain. But of course, we definitely need to think outside of the box instead of thinking multidisciplinary, instead of just one siloed discipline. I mean, in my group, that's what I'd like to do. You know, marrying control with communication, with machine learning, with game theory. I mean, I think this is the best way, even for an institute like yours. That would be the best thing to do. Yeah, that's my opinion.
Okay, thank you. Jean?
Yes, I will avoid, repeating, because I think it was said that I think what you can, based on the list of areas that you read before, you can have some good multidisciplinarity and interdisciplinarity in approaching problems. So I think maybe, the challenge is to make researchers, get out of their comfort zones sometimes, organize meetings with multiple groups and help people, understand the problem of others. So if you really understand what is the problem in pattern matching, right, or machine learning, and what do these people need from the networking perspective or from the architecture perspective, that is helping the research of the networking people, and vice versa. So I would say if you can, make researchers get out of their comfort zones and hold planned interdisciplinary and multidisciplinary meetings, that would be to their own benefit and to the benefit of the institution. That's my take.
Okay, thank you. And that leads precisely to my next question. That is, our group, Telecommunications and Multimedia, has well-established relationship with other research groups and companies that work, for instance, in domains of electrical smart grids, robotics, industry, or else. You know, all of you, that 5G and 6G, they use this concept of verticals, which consist of communication networks and services designed precisely for these domains. That is for smart grids, for robotics, for industry, or for else. How, from your point of view, could the edge intelligence be used to strengthen joint research with these domains? And how can edge intelligence be used to help define better verticals so that we could, let me say, provide better networks which are well adapted to industry, to smart grids, to robotics, to else? In which way could we do that? Maybe now we could start by André.
Okay, Manuel, thank you. I think so. Those verticals, of course, are in a sense market oriented. in terms of technical aspects, I think the more important are the volumes and the edge processing power that is required. But taking in consideration that a lot of the nowadays architectures are based on deep learning and CNNs and stuff like that, as was presented by my colleagues, I think we have the capability of having edge computing devices with those architectures and that are accelerated and can work on real time on whatever vertical it is. So I think in a sense, the market will come with that differentiation. I think the operators will try to push those verticals and the larger clients that they have in order to try to have the first solutions coming up in the next few years. That's my opinion.
Okay, thank you. Mehdi, please, if you
I mean, for the question, I mean, I think it all starts from the requirements. If your data is distributed, right, across the network, if your concerns is privacy, then of course things like federated learning, other techniques are a must. You cannot do without it. So here, even in OLU, we have been actually exploring how to use federated learning in the healthcare domain, having multiple hospitals trying to collaboratively train a model without sharing the private data of patients. As you know, it's not possible, right? So typically what they used to do is to encrypt the data, put it in a server, and hire lawyers and spend 1 year to write down the document how to share the data. Federated learning solves you the problem. Of course, it doesn't solve it all the way, because federated learning is missing the aspect of what we call personalization. Personalization is very hard to do, right? But we also can see application in manufacturing. Actually, I have an EU project now precisely looking at collaborative robots using again federated learning, meta learning. Agriculture, we are seeing applications with tractors, for example, trying to share this intelligence. Because what's edge AI? I mean, simple terms is just sharing knowledge across different actors. Those could be hospitals, could be base stations, could be sensors, could be whatever you want, right? And then the constraint is it latency? Is it privacy? Is it reliability? Is it bandwidth? Is it all of them, right? So, I mean, this is a bit, I mean, at least how I see this edge AI play, but it could revolutionize everything, everything. Yeah.
Okay, Jean, you gave us some examples on industry. Would like to elaborate a little bit more?
Yeah, without disagreeing with the previous colleagues, I would say, that the verticals are same, but different. Why I'm saying this? Of course, the core technology is the same, right? Federated learning or 5G and so on. But if you deal with real problems, right? You don't just want to make a proof of concept in the lab and that's it, right? And then each industry has its own requirements, because some industries are more conservative in the digitization. For example, manufacturing is completely different from finance and banking, right? Because there are different cultures, different mentalities, different levels of digital transformation. But also, when you solve the problems, you need to have an understanding of the business requirements of the problem. And a typical example is machine learning, right? Or deep learning. When you work with machine learning, you need to have this so-called domain knowledge. So, you can see a pattern, you can find a pattern, you can find a rule. You need to understand whether this really makes sense in the real world, because sometimes we find patterns in machine learning which are not useful, right? Or are biased or have nothing to do with the real world. So there is some point, especially when you start delving into the real aspects of problems, where you need the domain knowledge and when you need to develop vertical experience, if you allow me. Industry is a classical example that maybe 60% is to understand the problem, right, and be able to formulate it, rather than building a deep neural network that you have many tools nowadays to do it. but being able to understand the problem is probably, you know, half of the story, right? And if you don't have people with experience, that they are some industrial engineers or have worked in Industry 4.0 in the past, it is really it has very big learning curve to start understanding the problem. So I would say, concluding, they are same. So you need to have certainly some generalist researchers on this technology. But if you want to attract funding, to be competitive, and to build some systems that you can connect to the industry, you have to have some specialists also, some people in the research team that they are more inclined in looking at a specific vertical.
Okay, thank you. Antonio, would you like to add something to this generic discussion?
Yeah, no, just an extra line, perhaps. I fully agree with what has been said in a way. So I think, from my point of view, edge AI and edge computing are going to have a massive impact, as everybody was saying, in industry and across all domains. But I think one key application or one key sector that is going to be driving this forward, we are all looking at industry and autonomous vehicles, but at the end of the day, I think one key sector is going to be the military and the defense and security. And in these systems, there are particular requirements which are important. For example, what they call SWAP, size, weight, and power. So I think this is going to be driven the technologies there, that they are small, reduced footprint, that they don't occupy space, that they can be deployed into an individual, that they consume less power. And with critical developments as well, the fact that the information has to be somehow encrypted when transmitted, so it cannot be retrieved by an enemy or by an adversary. And perhaps systems, a lot of them, that will not be connected to the network, and that can operate on their own. Okay, precisely to reduce processing requirements, but at the same time to have the ability to, if a network or a system is attacked, then the attacker basically drops down, that the technology can still operate. So I think that's also something that has key implications for the military. But looking forward, what the pandemic has told us, and I think this is going to have critical challenges for our society going forward, there is a lot of investment going to be in something called resilience. The pandemic has told us that we think we are modern societies, that we can deal with everything that falls upon us, but that's actually not true. The pandemic came and we're all in our houses, not doing really anything, and a lot of people has died. And societies have been put to they have brought to the stretch. So I think there is a lot of effort going to be developed to systems that are resilient, and that is going to be a critical aspect of future technologies, including HI. I think that's an aspect that we need to consider, all of us, not only from security applications, but more widely for systems like power networks or autonomous vehicles, that the systems can still be able to operate more or less without everything going to a cataclysmic disaster if a major event happens.
Okay, thank you very much.
Yeah, also Manuel and Antonio, I think on this point, it's important to say that there is a decision from NATO, right, and United States, right, since 5 years or more, that European Union has to increase its military spending, and this involves a great deal of research, right? And in Brussels, we have the European Defense Agency, which is growing bigger and bigger, and is creating a lot of research programs in areas like resilience, situation awareness, security, and so on. So I think there are a lot of good research opportunities and funding in the defense and military sector in Europe.
I guess,
thank you.
I fully agree. If I might just interject quickly, I would just say that all these developments that happen in the military at first, which is obviously a very big source of funding for research, because they are very good at uptaking new technologies, they always trickle down to civil society very, very quickly. Or, I mean, maybe not that quickly, but they do trickle down. So in a way, these research developments are driven by them, but they will benefit civil society no matter what.
Antonio, you're talking about DARPA, for example, in the United States, right? This is how it works there. In Europe, we didn't have a DARPA, right? We are building now, sort of an agency like this. So I think this model will happen here as well.
Yeah, I agree.
Okay, let me put another question. That is, this concept of edge intelligence based on machine learning, it is, everybody is discussing it and working on that. But what do you think? Do you think this concept will definitely enter in our systems, or could it be a trend that may disappear with time? What is your personal impression about that? Maybe now you can start with Mehdi.
Yeah, so to me, the trend is here to stay. I mean, if you check all the 6G visions today, Nokia, Ericsson, Huawei, Samsung, Edge AI is #1, because essentially, again, it's the way to go, right? I think maybe also lack. I mean, if you ask me what's novel, I mean, with respect to 5G, I mean, it's all of the same, right? So now we think of connecting intelligence, the new, roadmap for what comes after 5G, because I mean, also it's unlike its predecessors. I mean, centralized machine learning. I mean, I'm not saying it's a solved problem, but new requirements, privacy, of course, everybody's aware of the GDPR and all that. New verticals or new applications such as autonomous vehicles. So you have to go to the edge, right? You have to push intelligence to the edge. Where I take issue with it is, again, as I mentioned in my talk, everybody's working on the topic. So we start to see kind of I don't know how to call it, a winter in terms of publications, in the sense that there's no innovation because we're just recycling all the research. And yeah, but I think what I tried to lay down in my last slide, this is definitely the way forward. There's no other way around it, because everybody can do statistical correlations. I can correlate the color of my shirt with the with the day of the week. I can train a model. I mean, so causality, very key. Robustness, generalization. These aspects will drive the next generation of edge AI. That's very clear, at least on my side. Yeah.
Okay, thank you. I believe that John will agree with this view as well.
Yeah. Well, I think what is not a trend, right, is doing things faster and better. So automation and intelligence. So in the business world, if there is a way to operate your factory or your warehouse faster in a more cost-effective way, you will take it. So it is not just a trend. So I think Edge AI will be an enabler to deliver this promise, right, of doing things faster, at less cost, with better quality, and with less labor. It's not going to be maybe the only one. It's going to be one, right? So we are going to, the cloud will be certainly into play. Also, other things are coming. Quantum computing, they may play a role, in the next 10 or 15 years. But all these, are enablers to increase the competitiveness and to give better products and services to the customers, industrial customers or end users. So they are here to stay. We need to embrace them and to go actually faster on them. And what is most important, we need to prepare many segments of the population that would be affected, right, by this. Because when you automate a factory, when you automate a warehouse, and you are able to operate it without, workers or with 20% of the personnel, some people are affected. So I think we should say that they are here to stay. They will probably accelerate, because this is what we are experiencing. We are experiencing technology acceleration. So things happen faster and faster, and we need to prepare the society for this and to protect whoever needs to be protected. That's my opinion.
Thank you. Antonio, would you like to add something?
Yeah, no, I fully agree. I mean, HAI or any other new technology, it's always the question whether it will have a radical impact, no, if it's just a hype. I don't think it is. I think a lot of research will be thrown on this field, and the good of it will remain, and the things that are perhaps less adaptable will fade away. So I think it's a natural thing that it's difficult to distinguish whether something is a hype or it's not a hype, because at the end of the day, things do stick if they are good, as John was saying. So I think there is no way back. Adding intelligence to the edge is a natural development. And you can call it intelligence, HAI, you can call it the way you want. But at the end of the day, adding functionalities that are useful and provide an advantage or provide extra value are always going to be welcome. So I do think that there is a need for that, and especially with the developments in the Internet of Things and in other technologies that will make it unavoidable. What shape or form will it take? It's difficult to say right now, but certainly something will do stick. Yeah, that's my view.
Thank you. Andre, please.
I also agree. So it's already a reality in some domains. For example, Mobileye, one of the players that is doing systems for vehicles, is already producing very powerful edge AI that can extract features from the road ahead and send only the labels and the GPS to the cloud in order to make the system GDPR compliant in a sense, and also for because of the bandwidth, and so I think it depends, of course, in the area, but it will stay for sure.
Okay, thank you. I have some more questions, but I think now is time to open discussion for the other attendees. So if you have some question that you'd like to discuss to any of our invited speakers, please put it on chat and let us know the people you'd like to answer to your question.
Use the raise hand function as well.
Okay, and in that case, the question could be placed not by text but by voice, is what you are suggesting? Any question? Well, I don't see any, so maybe I'm going to put another question which is related to telecom infrastructure. So edge intelligence by placing, as you have mentioned it in your presentations, more intelligence on the edge devices and taking advantage of fog as well. Well, maybe it will impact on the current telecom infrastructure. So how do you think it will be the impact of this technology on current telecom infrastructure from the point of view of its architecture? Will the telecom infrastructure change drastically because of this edge intelligence thing? Maybe you could start by John.
Yeah, it's a good question. Actually, you know, I'm not going to, I will convey mostly a business experience I have. So, you know, for example, in Greece, where I'm based, you know, currently right now, the government has been quite quick, you know, in licensing, right, the spectrum for 5G and so on. So, but still, you know, speaking with the C-level executives of the telcos, they are not 100% sure, you know, that they have the right business model to make money, right, out of 5G, because apparently it's not the application of this new telecom infrastructure is it shouldn't be, you know, just about faster web browsing, right? That's not enough as a business model, right? Maybe it will bring some revenue. So I would say that certainly we will see the infrastructures of the telcos evolving to 5G. This is already happening. It's commercial in some countries, and others will follow, and maybe a few years later to what is now called 6G. But the pace will be also driven by the money, in my opinion, which means that if they can really find the right monetization, the right use cases from the industry, right? So if, you know, the factories, the critical infrastructure operators come with user-driven needs and then tell to the telcos, yes, we need this private 5G network, right? Because this is essential for our business operations and business continuity. So my answer is that it will happen, and we will see an evolution of the telecommunication infrastructure. Always there is a legacy compliance. So 4G, LTE will be also around, and of course, transitional solutions. But the pace, the speed of the evolution of the telecommunication architecture will also depend on the money flows and on whether, you know, the telcos believe that they have business cases to make money on the new networks.
Mm-hmm.
And I'm not speaking.
Thank you. Antonio, would you like to add something?
Yeah, obviously, I guess the point that comes to mind is that whenever a new technology comes in, at the end of the day, what happens, or especially in these fields, is that even if everything is to become more efficient or better or consume less energy, the sad truth of it is that it turns out that it ends up provoking more data traffic and increasing traffic or generating more demand, basically. So I guess my thought on this is that with all this edge AI, there will be an increased demand on data to be transmitted, and certainly that will have an impact on the architectures and the technologies that are required. From a long-haul communication perspective, optical communications, there will be an increased demand of data to be transmitted, and that will impact on data center technology. And from a mobile networks or wireless communications, that obviously you will have more devices transmitting more data, perhaps, or more functionalities to be dealt with. So that will impose higher bandwidths and more demand. So the systems will need to keep up. So it's a question of going to other frequency ranges, or increasing capacity, or new modulation formats, or going to optical wireless systems, or there might be other technologies. But certainly there will be an increase on demand, and that will have to be dealt with. That's what I think will happen.
Andre, is your turn?
Yeah, so of course, I think the complexity will increase because I admit, for example, considering the automotive scenario, that the edge processing power and has to be so spread over a lot of by a big area, and so challenges are going to be, of course, big in that scenario, and of course we are here to answer to them, and you are probably better positioned for being part of that. Thank you.
Okay, thank you. Mehdi, what is your view?
Maybe I can just
based on all that you have from this big 6G project as well, that discuss it in detail.
Yeah, sure. Yeah, so of course, yeah. So maybe what I can mention is that maybe the big elephant in the room, sort of speak, in all the edge AI, and also even in the application of AI in the wireless domain, because we've seen a lot of it recently. The main bottleneck is energy, power, sustainability. So as you know, sustainability is a big deal now in Europe, right? The Green Deal and this and that. Essentially because we realize our model training are very energy hungry. If you put a hearing aid here and it burns your ear, I don't think it's gonna be good. In other words, yes, energy power to me personally is number one, because essentially edge AI technology is already here. You can argue it was already here 4 years ago, because what's edge AI? You just taking a bunch of data centers, putting them closer, putting them in the factory. That's edge AI. But really the big picture here is to be able to reduce drastically the energy footprint, the energy bill. Here in Finland, they did a study, maybe I'm sure it's similar in Europe, is many of the trucks or lorries that travel across borders, they are, most of them are empty, right? So that has a big impact on the CO2 emission and all the related aspects. So energy. So in the 6G flagship that we have in Oulu, energy is number one on the agenda. Of course, the rest, maybe is this terahertz, bands. Of course, again, driven by the need to go for higher and higher frequency. But there's a third one which actually not much known to the public, perhaps, but will be a bit more known in the near future, hopefully, is the notion of semantics. So even in communication and in edge AI, still, what we are transmitting is either the raw data. We said it's not good for privacy. We said, no, let's transmit a model. The problem with that model is not semantic. There's no meaning carried out or transmitted between the device. And now if you go back to Shannon, Claude Shannon, 1948, there's a nice paper there which laid down the fundamentals of communication. And actually, it turns out we focused from 1G to 5G on a small, tiny definition of communication, which removed context. It removed meaning. 6G will be the technology that will bring back the meaning, because if we transmit the meaning, as I said before, transmit much less, much more energy efficient, and so on and so forth. Basically, how the human being operates.
Nice view. I don't know if some of my colleagues would like to add something to this panel. We still have, I'd say, some 2 or 3 more minutes. If not, I think I'm going to close this very nice discussion. It has been very good. You brought us fresh views and perspectives that for sure we are going to consider and to discuss internally. Of course, there is a big opportunity for all of us to carry out research together with our partners and addressing these very challenges that are appearing associated to 6G. So thank you all very much for being here and discussing this topic with us. So that's it. Luís Pessoa, I'm returning the session to you.
Yeah, thank you.
Thank you.
At this moment, so before concluding this meeting, I invite everyone for a group photo. So I invite everyone to turn on their cameras if you are comfortable with it, so that we can get a group photo of this meeting for the posteriority. Okay, thank you. Very nice. So my colleagues are probably already shooting the picture. It's done?
Yes, it's done.
Okay, thank you very much. Okay, so now we can move forward to the conclusion, to the closure part that Manuel Ricardo will bring his final thoughts to conclude this meeting. So Manuel, please.
Okay, so I think that this open day has really been very interesting. So the theme that has been selected towards 6G enabled by edge intelligence is opportune, and it aggregates well the research that we carry out at CTM. The model that you have selected as well, it is very interesting. So we put together some relevant internal works and combined these presentations with the presentation from our outstanding keynote speakers that brought us very excellent views, and also the number and variety of participants that we have in the meeting. I believe that we were more than 60. It demonstrates the CTM relevance and importance of CTM for INESC Tech. We started it by CTM coordination, which has presented its vision of edge intelligence, very fresh and good vision from my perspective. It's accuracy for efficiency, privacy, low latency, and presented the edge intelligence as the enabler, as a major enabler for 6G. And very importantly, it showed us how the current CTM vision, mission, and research lines are very well aligned with this edge computing for 6G theme. The internal select works that have been presented, they also revealed the diversity and potential that we have at CTM to carry out this type of research. So INESC showed us how edge computing can be applied to biometrics and well-being, how it enables reporting in real time, and how it potentiates detection of counterfeit biometric data. Teresa Andrade gave us a fresh perspective on research and standardization on the Internet of Multimedia things concept, and has identified types of objects and their communication and computing requirements. And it has mentioned the point which is important, is multi-point to point concept that should be taken into account. Eduardo Almeida showed us how deep reinforcement learning can be used to deploy UAB-based wireless access points. It demonstrates how fast learning process can be, and it also addresses an important thing that has also been stressed on some other presentations, that is the relevance of combining learning techniques with discrete event simulation. That the simulation has to be together with learning techniques. And Vitor Tavares, they brought us these main registers for neuromorphic computing and showed us how to bring low cost in memory computing by integrating in the single technology, memory nano device and transistors. Showed us, at least to me, a new world. So it has, from my perspective, an excellent combination of works, and it showed very well the potential we have, and it is left to be combined and explored. In turn, our outstanding invite keynote speakers, they gave us very good visions, which will be excellent food for us to discuss internally and in partnership with our partners, of course. So Antonio Hurtado showed us how brain-like photonics is enabling computing and artificial intelligence by describing how laser neurons can be used to emulate neural circuits and ultra-fast speeds. And then Lorenz showed us how to monitor physiological signals and combine them with contexts, important, and how to integrate these techniques in the industry by describing relevant paths that grows from science to innovation. Mehdi described how artificial intelligence will enable 6G wireless communication by taking advantage of distributed and communication efficient machine learning over wireless network. And he showed us federated and split learning, and importantly, the next frontier on edge artificial intelligence by these challenges and limitations that he has presented on his last slide. John Soldatus outlined the merits of edge computing for emerging IoT and applications, and discussed these merits from different perspectives and paradigms in context of current and future networking infrastructure. So its application industry has been revealed. So on the other hand, this panel, they brought us some new ideas on how to use edge intelligence to increase research cooperation, not only among our internal groups, but also in context of other research groups to which we collaborate, and that, let me say, that this joint research can be put together in what we call these verticals, and we can see that there are many opportunities. So there are a general approach that on edge intelligence that can be taken for all these application scenario, for all these verticals or slicing way of doing communication networks, but there are certain domain know-how that has to be considered, and so there is for sure an opportunity for all of us. So overall, I think it has been an excellent workshop, and I think it should motivate us, let me say, to refresh our vision and, who knows, our branding. James showed us that our vision is fully aligned, but maybe we should discuss it, because there are this new machine learning trend that I think we should look at it and revisit what we have done and what we have at the moment. I think we should define long-term and joint objectives for our research, in which we can put all CTM research areas and define a strategy that enable the combination these research areas in which we excel. And important, we can do that in cooperation with our research partners. From my point of view, this area of 6G enabled by edge intelligence, it has an enormous potential. And more than that, it has been defined as a strategic area by the Board of Administration of INESC Tech, not only because of its potential. You know that communications is having let me say, kind of revolution. So 6G will be, these smart networks will be something very different from the previous generations, but also because this new way of doing communications will have a strong impact on key research areas of our institute. So we are well known for our activity on smart grids, on industry, on NELs, on C, and so on. And communications is key, is important for this research area. So this is very important for the institute. And so because of that, I think together we should define a sound strategic plan to address this topic of 6G enabled by edge intelligence. And after we have this plan, for sure we will find the resources we need to implement it by the times we are living, and with so much amount of funding available, there will be for sure no difficulty for implementing this plan. I'd like to give a word for our students. I don't know if we have many of them attending the Open Day now, but you know, as someone has mentioned as well, last year we are not having many students selecting communication or multimedia for advanced studies. I hope that this workshop has contributed to show that our research areas are full of opportunities and that there is a revolution in the air. And so we need urgently these students to help us to craft these new smart networks of the future, this intelligent network internet that we are going to have. I'd like to finish to deeply thank our keynote speakers, Antonio, Andre, Mehdi, and John, for their excellent visions and contributions. Our colleagues Anna, Teresa, Eduardo, and Victor for their presentation that have revealed what the best we have at CTM. The audience, including our researchers, students, and research partners, for attending and helping us define our future. CTM coordination, including the area leaders, for their strategic vision and leadership, which identify new research paths at INESC Tech. And finally, the organizers, Luis, Américo, João, and Elder, for organizing this event for CTM and for INESC Tech. So thank you all for that. And I hope we can define new research avenues based on things that we have discussed. Thank you.
Thank you, Manuel Ricard, for moderating the discussion and for this this excellent summary and the highlights in the end. Okay, thank you.
Thank you all in the name of the organizing committee. So I thank you all and hope to see you at some next event. In the next year, we will have again the Open Day CTM, so we hope to see you again. Thank you.